Day 2 of International Symposium on Synthesis and Characterization of Smart Material and their Potential Applications. The invited speakers for the day are Professor Ashok Mulchandani from the Department of Chemical and Environmental Engineering, University of California, USA, Professor Absar Ahmad, Director, Interdisciplinary Nanotechnology Center, Aligarh Muslim University, Professor Mahendra D. Shirsat, Department of Physics, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad, and Professor Neeraj Khare, Department of Physics, Indian Institute of Technology, Delhi. It's an honor to have you all with us today. On behalf of USBAS, I thank you for accepting our invitation. We look forward to hearing your talks. The session chairperson today is Professor Anindya Datta. Professor Datta is a professor of physics and nanoscience and technology in University School of Basic and Applied Sciences, Guru Gobind Singh Indraprastha University. He did his master's in physics from IIT Kharagpur, his PhD from Indian Association for the Cultivation of Sciences, Kolkata, the oldest research institute in India. He did his postdoctoral study from IACS and Academia Sinica, Taiwan. Prior to joining GGSIPU, he was at IACS, Kolkata. With a research career of over 27 years, his interest was always nanoscience and technology. His current research interest is two-dimensional material and their composites. He has publications in a wide variety of journals. I request Professor Datta to please conduct this session for today. Professor Datta, please.
Am I audible?
Yes, you are. You're audible.
Thank you, Shipra, for your kind introduction. So we shall be starting. Good morning to everybody. We shall be starting our morning session today. And our first speaker is Professor Ashok Mulchandani. He is a distinguished professor of chemical and environmental engineering and W. Reuel Johnson Chair in Environmental Engineering in UCR. Professor Mulchandani joined UCR in 1991 as founding and pioneering faculty in Barnes College of Engineering. From 2000 to 2004, he served as the chair of the Department of Chemical and Environmental Engineering. He is a fellow of the American Association for the Advancement of Science and the American Institute for Medical and Biological Engineering. From 2001 to 2015, he was editor-in-chief of Applied Biochemistry and Biotechnology. He is a member of editorial boards of several journals. Professor Mulchandani has published over 300 peer-reviewed journal publications, 15 book chapters, edited 4 books, and delivered several plenary keynote and invite talks. He has more than 20,000 citations with a very high H index of 78. His research focuses on the emerging area of bio-nanotechnology, primarily creating sensors and devices that use biological and or chemical sensing elements to analyze the chemical or biological molecules with application in healthcare, environmental monitoring, personal and homeland security, food safety. With this short introduction, I'll request Professor Mulchandani to start his talk for today's event. Professor Mulchandani, sir.
Professor Mulchandani, please unmute yourself.
It's unmuted now?
Yes, yes, we can hear you.
Okay. Thank you, Professor Datta, for the kind introduction. And I appreciate very much the opportunity to speak to you all. So I need to share the content now.
Yes, please.
Okay, are you able to see the screen?
Yeah.
Okay.
We can see.
Okay, so I also want to thank Professor Rajesh for the invitation to meet all of you through this remote system, sitting at home, close to my bedtime, feeling sleepy, but awake enough to make some sense in my talk. Hopefully, I would not make you sleep while I try to keep awake. Okay, so let's see about that. As I was saying earlier, that when Professor Datta was speaking, there was sort of breaking up of the speech. Are you able to hear me properly? Or do I need to slow down even further so that it is not
Here you
breaking? You can hear me properly?
Yes.
Okay. So my title of the talk, which is showing up in front of you, is Two-Dimensional Nanomaterials-Based Bio and Chemical Sensors. I know I have about half an hour to give the talk, and I see that I've already been cut down by 7 minutes, so I don't know whether I still have 30 minutes to give my talk or 30 minutes is total. That is going to depend upon, so please just give me a hint and I can stop it anytime you want. Okay, just don't have to go through all of it. So my screen is not advancing. What should I do? Technical help.
There's an option in the left side corner of your screen to change the slide. Bottom corner.
There's no bottom because I'm seeing only my slide and I'm seeing myself in the video and I'm seeing only the organizing thing but it is not moving.
The option will be there in the bottom side of your screen. Here.
Okay, bottom side of the screen, that's the advance. Okay, so I have to use that one to advance, not my space bar or anything like that?
No, it's an option like this only in WebEx.
Okay, thank you for. Okay, so since my title of the talk was saying that I'm going to be presenting something related to 2D materials-based chemical and biological sensors, I just want to give you a perspective of why my research is continuing to work in the area of sensors and biosensors. But there are two categories of sensors. I don't have time to go in differentiating it. One called biosensors. They mainly are sensors that use some kind of a biological recognition molecule to detect analytes of interest. As the introduction by Dr. Datta was mentioning, that my interest being in chemical and environmental engineering is trying to sense chemical and biological molecules. I'm not interested in sensing physical parameters like temperature, pressure, velocity, those type of things. So we use biosensors as one of the ways of increasing the selectivity and the specificity. And the most widely used biosensor that anyone can think about is the diabetes test that everyone who has diabetes is doing it these days in home, or glucose sensing, pregnancy tests. Those are all biosensors. And there's a growing market for these sensors. As you can look at the graph below, roughly in 2019, the market was roughly about $20 billion worldwide, and it's expected to grow to about 30 billion in another 4 or 5 years. The other group of sensors that is more like chemical sensors, which do not use biological recognition molecule, but can still use some kind of a recognition element, could be metal nanoparticles, could be two-dimensional nanomaterials, whatever it could be, considered to be for detection of, once again, chemicals or contaminants in air, for agriculture, for automotive gases. Okay, so they are lumped under gas sensors. There is a big field of gas sensors coming in the market for detection of diseases through breath analysis, and so that's what the disease detection is categorizing there. This market is relatively smaller compared to biosensors, but still in about $1 billion or so. So there's a growing need for sensors, and my research interest is trying to develop nanosensors. So the question to be asked is why nanosensors, and why there is a big interest in the field of nanosensors. And the reason is listed here on this slide. These nanosensors can be made out of any type of nanomaterials which has one of its dimension less than 100 nanometers. That's the definition of nanomaterials recognized internationally. So these materials could be 0 dimension, 1 dimension, and 2 dimension. My research group has worked a lot on one-dimensional nanomaterials like carbon nanotubes, conducting polymer nanowires, nanobelts, and other stuff. And here's the picture showing the one of the biosensors that we had developed for detection of microRNA using carbon nanotubes as the transducer. The other material that I'm going to talk about today, and we started working on this maybe about 10 years back, starting with graphene. And this is a picture of our CVD-grown graphene monolayer. CVD stands for chemical vapor deposition. So we made very, very pure two-dimensional graphene. Where can I see the arrow now? Because my arrow is missed now. Okay. So my research group is interested in the synthesis, characterization, and then application of nanomaterials. We do synthesis of these nanomaterials primarily by two techniques. One is either electrochemical and or chemical vapor deposition. We can go into the other areas of synthesis, but that's unusual in our lab because we are so happy with these two approaches because of the quality of material we get. So we have focused on these materials. Then once the material is synthesized, we want to make sure that they have the right characteristics. So we spend a lot of time in characterizing them using microscopy, spectroscopy, and those are the techniques that are shown on the right-hand side. And then we go into the clean room if necessary and make devices, combine it with our sensing platform, and then use it for various detection things. So those are the goals. They can be for gas sensing, for sensing of contaminants in water, food, environment, okay, healthcare, name it, and we are in that field looking at those different applications. So a particular type of sensing platform, because I didn't have time to go into trying to describe to you the components of a sensor. So sensor consists of three components. One is the sensing element, second one is the transducer, and third one is the amplification electronics afterwards. So what is this sensor showing you is a platform in which we use the transistor or a chemiresistor-based sensor. It consists of, like a usual transistor for physicists, it's a very common thing, a source electrode and a drain electrode separated by a small gap. And in that gap is a semiconductor material. In the case of sensor, this semiconductor material could be sensing element itself, which is what I'm going to be using, or we can modify this semiconductor material with some other kind of a sensing element, like maybe bioreceptor, and a second example that I'm going to show you. And the reason why we've been so happy and we have focused on working with these field effect transistor or chemiresistor, primarily chemiresistor. Once again, this picture is a chemiresistor and not a field effect transistor because I'm not showing any back gate or any top gate in there, okay? So we work primarily with chemiresistor because its structure is simple, the operation is simple, They work very simply by measuring the change in electrical resistance due to the interaction between the sensing material and the analyte at the surface of the sensing element. So that's what we do. Okay, and in this case, the sensing element could be a 2D nanomaterial. So as I said earlier, the first sensing element that the first 2D material we started working with, or 2D material as sensor, we started working with was graphene. And we got enamored with graphene the same way as many of the physicists and electrical engineers all felt so overwhelmed by the graphene because of its properties as listed here. High charge carrier mobility, charge carrier density, electron mobility, thermal conductivity, strength, and all those things. And they all felt like, okay, this is now a wonder material that's going to solve the problem of shrinking the size of the transistor to what we want now to pack more and more transistors into our computing power. But unfortunately, as the research continued, all that enthusiasm was sort of put aside because it so turns out that graphene is a zero band gap material, or basically a semi-metallic. It's not a semiconductor. And so my approach of trying to use it as a transistor to look at the small changes of resistance or conductance due to the interaction between the analyte and the surface of graphene, not going to be very easy to do unless and until I was going to do a full sweep of the gate voltage and look at the direct voltage or the direct point shift. And that is what most of the people working on sensors decided to do to salvage their research. Some others decided to start band gap engineering, and a couple of different methods of band gap engineering we also tried. One is to make nanoribbons. Instead of making nanoribbons, we started to make nanomesh, so that we were going to look at much bigger surface as opposed to thin strips of nanoribbons. Secondly, is to introduce defects to introduce band gap. But when you introduce defects, you lose the conductivity of the material, the charge mobility, and other stuff. So even though you do introduce band gap by doing this band gap engineering, unfortunately, it's not the right approach to take. And so as most of the physicists and chemists and engineers started going back into their periodic tables to figure out what is the alternative to graphene, what are the other two-dimensional van der Waal type of materials that we can use for transistors, the ones that were identified to be the easiest one to approach were these TMDC materials, or transition metal dichalcogenides. And there are a range of it showing in this periodic table combination. The first one that most of the people have been working on, and we started working on too, is molybdenum sulfide. But this time, before we ventured into trying to jump into doing something with molybdenum sulfide, we decided to make sure that we were not going to be disappointed one more time. And as we did the investigation into the details of the material properties, we found that the issue with semiconductor MOS2 is not going to be resolved by simply using MOS2 instead of graphene. While MOS2 does have very useful and helpful properties of low band gap, 1.87 electron volt and direct band gap, it has a good on-off ratio as shown in that figure on the right-hand side, which graphene doesn't have because of its semi-metallic nature. Unfortunately, it is very high resistance. Its resistivity is very, very high. And so what happens then is that you have very low background signal. So the issue is now that we do get extremely low signal. And then also we have an issue with Schottky barrier, which is shown here when you have different work function materials put together, like which we'll have to do to make a device, because we have to put contact electrodes on the top of our of our MOS2 layer. So we were a little more cautious this time, and we decided not to jump into with both our feet into the testing of sensors based on MOS2 alone. We decided to take a different approach than most of the people who are trying to again do many different ways of working with MOS2. We decided to work on heterostructure. We said, let's try to combine the good properties of graphene and good properties of MOS2 and eliminate their bad properties and see whether we can create a heterostructure which is going to be in this region in the middle. And thereby we can take advantage of the properties of semiconductor of MOS2, good conductivity of graphene, and see whether we can build some good sensors based on this approach. And so this is what my talk for the remainder of the presentation would be, is to try to build these devices. We want to build devices based on materials that could be easily scaled up. So we never really want to work with materials which physicists and electrical engineers are very happy to work with, which is exfoliation. I think that exfoliation is good for lab testing and other stuff, but not for manufacturing. And so we usually use chemical vapor deposition methods to grow. Both the methods of growing graphene and MOS2 are well established and well reported in literature. We did the same. We use chemical vapor deposition of methane cracked onto a copper catalyst for the graphene. And for MOS2, we combined, did the CVD of molybdenum oxide and it reacted with sulfur vapors, and then deposited the vapors of MOS2 onto sapphire. And from sapphire, we lifted it off and created single layer sheets. So, and then we go ahead and stack them up to make structures. So there are two types of structures we investigated. The first structure was our naivety and said the simplest one would be to try to take advantage of the conductivity of graphene and put graphene as the underneath layer. Secondly, also when people use graphene as the sensing layer for contaminants in air, there is a big drift of graphene due to the absorption of oxygen and other elements or other chemicals that absorb on the surface of graphene. So there is always a sensor drift. So we thought of, okay, as compared to that, molybdenum sulfide is more stable. So what we will do is we will put the underneath layer of graphene to have good conductivity channel. And on the top of that, we are going to put MOS2. And let's see what happens when we have a heterostructure like this. So there are advantages of such heterostructure. Okay, what as a chemical engineer, I was only looking for is a good sensing. But before we venture into sensing, we need to make sure we do the characterization of material. We characterized the heterostructure and compared the properties of the pristine materials, which is pristine MOS2 and pristine graphene versus heterostructure, and concluded that we did indeed have a heterostructure in which the two materials were interacting with one another. And those interactions were observed through the shift of the G band of the graphene and the quenching of the photoluminescence shown in figure B. Figure A is the Raman. And both of these confirm that, in fact, we are having a good interaction, and they were working in tandem. In fact, MOS2 was donating electrons into, in fact, it was N-doping graphene, which was heavily P-doped to begin with. And this confirmation of the N-doping of the MOS2, or N-doping of the graphene by MOS2 of P-doped graphene. Once again, I want to make sure I don't have a question afterwards that the reason why we get pretty highly doped P-doped graphene in our CVD synthesis is twofold. One is because when we do the transfer using ferric chloride and PMMA for the process of etching and transfer, and oxygen for etching, it introduces P-doping, okay? And so we do get pretty highly P-doped graphene and then the heterostructure shows a clear end-doping of that graphene. So one of the things that we claimed in this work that was published in Carbon was that this is a simple way of end-doping graphene or creating a p-n junction transistor or diode that you are interested in making. And so that is one of the advantage of using graphene MOS2 heterostructure. And we also wanted to make sure that our work function band gap diagram or work function diagram was going to be able to answer some of the things that we found. I would not go into the details of this, just to tell you that we did measure the work functions of all the materials. That means pristine graphene, pristine MOS2, and the heterostructure. And based on this, the left-hand side shows the work function and the Fermi levels for the MOS2 and graphene, and the right side shows the heterostructure, which shows that there is a electron donation from the MOS2 to the graphene, thereby end-doping the graphene through the process of heterostructure formation. And then simply we tested whether our heterostructure was performing better for some sensing application. I stole some of the ideas from Mahendra, who works a lot on, Professor Shirsat, who works a lot on VOC. So we decided to test toluene as the VOC. And the results here clearly show that compared to the graphene or compared to MOS2 alone, the heterostructure had a better signal to noise ratio, had a better sensitivity, and it did show that having a heterostructure did provide better sensing characteristic over the native materials. So our first question was answered. The second thing we wanted to do was to look at trying to lower the Schottky barrier between the MOS2 or graphene and MOS2 and the gold and MOS2. Okay, so to do so, we decided to look at a second design, which is design number 2, where instead of usually people use is they put the gold electrodes on the top of MOS2. So it is big work function difference between the gold and MOS2. We thought of why not we just take advantage of the fact that we have graphene, which is a good conductive material. And as I said earlier, it's a semi-metallic. So why not just use a 2D junction, 2D material of MOS2, 2D material of graphene, and create contact electrodes made out of graphene, and then see what type of benefits we get by creating this type of a design in which our MOS2 is going to be bridging the gap between the graphene electrodes. And this source and drain electrodes are basically graphene electrodes that are now with the contact pads. To mitigate the Schottky barrier due to the adjustable work function of graphene. And as our first test to show that there is a benefit of putting graphene as the source and drain electrode versus the gold electrodes. Here's the IV curve for this particular platform, and you can see the currents are in picoamps. When we move this into a graphene source drain electrode, you can see the currents are in nanoamps. So we have roughly a 50 times or 50-fold improvement in the or decrease of the resistance when we use graphene as the source drain electrode versus the gold as the source drain electrode. So we have already a good indication that Schottky barrier is reduced, and thereby we will get benefit. A second advantage we wanted to take of the property of MOS2, low band gap, was to use photo gating as opposed to the back gating or electrical gating or ionic gating, which is the other form of gating which is used in biosensing applications. And MOS2, as I said, has a low band gap of 1.8 electron volt and can be easily, the photonic excitation can be easily achieved with red light. In this case, we used a LED of red light corresponding to 650 nanometers wavelength. And once again, you can see the benefit of light over dark, both in the case of just the gold electrodes with MOS2 as the semiconductor channel, or the graphene electrodes with the MOS2 as the semiconducting channel. Okay, this is the dark current, that's the photocurrent. And once again, comparing the photocurrent versus photocurrent, you can still see a very high current output, which is telling you that the conductivity of MOS2 is improved by using this platform. So having achieved some of the goals of lowering the Schottky barrier, doing optical gating, we decided to apply this particular platform for detection of NO2s, simply as opposed to toluene, because toluene is working with toluene was not that easy for us, because generating different concentration vapors is tedious. So we decided to look at the MOS2 for NO2 sensing. It has been reported it's a good sensing element for nitrogen dioxide gas. And here's a comparison right now for the gold electrode, not the graphene electrode, the gold electrode, okay, with the MOS2 channel, and with and without light for different concentrations of nitrogen dioxide, 25 parts per billion, 50, 100, 150, and 200. You do see a concentration dependent response and a very significantly amplified response over the dark current. So this is a simple way of making highly sensitive sensor by using simple, and the principle of electronic detection is shown here. If you are interested, you can read it in the paper. Because of shortage of time, I see that I'm already past the 10:30 mark for you, or 11 o'clock mark for you, I should say. I'm just going to summarize it here and say that we have the very high. So here's a sort of a comparison of all the NO2 sensing we did. The sensitivity of the gold MOS2, gold with the light, is higher than the graphene MOS2 graphene, but the limit of detection is better for the other one. And the reason for that is because if you had paid attention, the signal to noise ratio here, okay, I don't have the figure showing the that figure that I was hoping to have here. The signal to noise ratio in the case of the graphene electrodes compared to just gold electrodes is much, much better. And so the limit of detection, which is defined as signal to noise ratio of 3, is much better for the last electrode as opposed to the gold, where the sensitivity is higher, but the limit of detection is slightly more. Okay, so do you want me to continue or should I stop? Is anyone going to respond to me? Do you want me to continue or should I stop?
Some biological detection will be good for us.
Pardon?
Some biological detection will be good for us.
Okay, so here's the biological detection one, which is the last third of my talk, or I should say last 20% of my talk. So as I said earlier, a biosensor uses a biological recognition molecule instead of just the MOS2. And an example shown here of biological sensing would be a MOS2 layer functionalized with a biological receptor, in this case, antibody. We may be able to use this antibody to detect COVID-19 antigen if possible. And that's what this antigen is. And so the principle is the same as I was describing earlier, is that when the antigen comes and binds to this antibody, which is very close to the surface of the semiconductor, it creates a change in the chemical environment near the surface, and that chemical environment is going to change the number of holes or number of electrons or whatever it is in the semiconductor material, okay, and thereby change the property of that material, which can then be correlated back. And so the traditional people do is they always, as I said, use exfoliated MOS2, which has several defects in it, okay, and then they attach the antibody using either the sulfide vacancies or sulfide defective sites, or salinize it, because salinization requires some kind of a molybdenum oxide, molybdenum hydroxide present there. And then they go ahead and try to use that, okay? And then usually, even after that, they have to use the method of sweeping the threshold, the gate potential. This one is showing the liquid ion gating method, in which the gate potential is swept and the shift in the threshold voltage of this gate potential is measured and then correlated to the concentration of the analyte. So that's traditionally the way they do it. We started trying to do the same thing. We said, okay, we'll start making the MOS2 device. We wanted to do graphene electrodes and then not gold electrodes. But before we even got to that point, we decided to check what is the result of this the FET curves that that people have been using for the purpose of sensing, which is shown here. These are the FET curves showing the source drain current versus the top gate potential. And they claim that with the increasing concentration, you can see these curve shifting. But in our experience, when we started doing that, what we found is that by just repeating the sweeps of the gate potential with time, 30 minutes, 60 minutes, 90 minutes, are without having any biological molecule there, we were still seeing a drop in the source drain current. So this is not due to sensing, but this is happening due to what we concluded was due to the delamination of MOS2 from the surface of silicon oxide, because the water was seeping underneath the MOS2 layer and lifting it off. And so this is not what we wanted to do. So to eliminate this problem, we decided to create a layer of aluminum oxide on the top of MOS2 using atomic layer deposition. A very thin layer of aluminum oxide of 30 nanometers were deposited. And then after testing the same thing as we were doing before, the FET characteristics at 30, 160, and 120, 30, 60, and 120 minutes, we found that we were not seeing any more that steep drop of the source drain current, indicating that the sensor was not seeping in the water and the delamination of MOS2 was going on. So our aluminum oxide layer was preventing this phenomenon. As well, the aluminum oxide also is a good way of immobilizing biological molecules using the chemistry of simple salinization. So you can salinize the aluminum oxide to create molecules that can then be linked to the antibodies. And also the aluminum oxide provided some benefit of a significantly higher current at the zero gate potential, which allowed us to then do the measurement in the true chemiresistive mode as opposed to FET mode. Because we like to work with chemiresistive, we don't want to sweep gate potentials, or we don't want to sort of do those type of things. So that's why this was what we decided to do. We used the salinization using aminopropyl trihydrosilane, and then using a bilinker called glutaraldehyde, attached not an antibody this case, but a DNA, single chain DNA, and then used it to detect the hybridization of a complementary DNA that was for the P53 gene for cancer, human cancer detection. And we showed that indeed we can do measurement both ways. We can do the measurement by either FET way or the chemiresistor way. And both ways are possible. And it is going to be easy to do on that. And it is a good sensor with a very good calibration, a very low down to picomolar detection limit for DNA, good selectivity for it was highly selective for complementary, but not for non-complementary DNA, which has either 2 base mismatch or 3 base mismatches. And that's a quick overview of this small biosensing work that I wanted to talk to you, and particularly the physicists and electrical engineers. And before I close my talk, I need to thank the people who participated in this work. These are the people who contributed to this 2D work, some of my funding agencies that funded this part of the work, and all of you who are patiently listening online and have probably now jotted down tons of questions, but maybe I did not leave enough time for you to ask questions anymore. Okay, thank you.
Thank you, Professor Mulchandani, for the wonderful talk you gave. And we all know graphene and MOS2 are two wonder materials, and you have shown us how to combine them, create a sensor in set configuration, and then to extend it with a cover of L2O3 for bio detection. And this is really wonderful. I'm sure our faculty and students will benefit great from this. I personally have a question. Means, what else other than MOS2 it can be used? This is number one. Number two, can it do something in early detection for something like COVID-19? Can you think something about that?
Okay. So the other TMDC materials that one can use, tungsten sulfide. Okay, so I showed you molybdenum sulfide. We are also working on molybdenum selenide. Okay, so those are the TMDC type of materials. There's a big interest these days in phosphorine, black phosphorus and other stuff. The reason is of these are all van der Waals type of materials, so that they can, and the reason why people are focusing on these things is because they can be easily made by exfoliation of bulk material. But there are many more other materials. Probably if you can grow by the CVD methods, maybe you can do so. And some of the other materials that we have used includes metal oxides like zinc oxide nanowires, conducting polymer nanowires. Okay, so there are a plethora of materials that are available. Only thing is, are they good, or are they will they be better than the existing materials? And lately, I have been probably sort of keeping these options open, but at the same time, looking at moving into some other materials that would be beneficial for combining into sensors. Okay, so they need to have some kind of also sensing characteristics. And now to your question about early detection of COVID. I do have ideas, and I did propose ideas, but unfortunately, they were not funded, so I'm not working on them. We talked about detecting antibodies against COVID in serum. Okay, but there are a lot of companies the companies are much faster moving than these universities. So before I could even propose something, they had a product out in the market. Okay, because my saying is that we all are intelligent people. We all think alike. We all probably think about similar ideas, because none of us are Einstein anymore. That we will be the only one who will have that singular idea that no one else would think about. So there are hundreds of people thinking about the same thing. Who gets onto it faster is going to be the successful person. So I wasn't the first one. Someone else took it, fine, that's good enough. At least I can say that my idea was not bad.
And now to student coordinator for some more questions, please.
Before you ask the question, I just want to give a shout out to my alumni, my Dr. Professor Tapan Sarkar, Tapan is there, just wave his hand.
Is there?
He was my PhD student. Yeah, he was my PhD student, and he's back at your institution. And so you have a good product from a good trained person. And I understand he got a good grant now to do some of the work that he so was eager to continue doing there.
He's listening to you. Is there? Amar or Vishnu, please take up the questions, please.
There is a question from Ali ma'am. Of MOS is predominantly present in
I'm not hearing you. Vishnu, I cannot hear you.
Sir, which phase of MOS2 is predominantly present in heterostructure?
You're not clear to me. Can you repeat again?
Which phase of MOS2 is predominantly there for this sensing?
This one is H phase, if I recall, because T phase is the more like metallic. So this is the semiconducting one. I think this is the H phase. I don't remember the top of my head. My student had written it down somewhere. Yeah, I think that. This one here. Yeah, it's the H. Hello? Are you hearing me?
Yes, we can.
Okay. Yeah, it's, you see in this table, it's like on the, okay, so we're using the material is our H phase, which is the stable one. Okay. Next question.
Yes, sir. We have one more question from the attendee. Is there any advantage of vertically grown dense nanowires in gas sensing than compared to thin film?
I cannot hear you properly. Can you do it one more time? Like last time you were clear.
Yes, sir. Is there any advantage of vertically grown dense nanowires in gas sensing than compared to thin films?
Will there be any advantage of growing vertically compared to horizontal?
No, sir. Vertically grown nanowires in gas sensing than compared to thin films.
Okay.
Instead of 2 dimension, if you have 1 dimension, what's the advantage or disadvantage? That's what he wants to know.
So as I said, like if you're going to use the example of 1 dimension would be, okay, if I use carbon nanotube versus graphene. Okay. So if I give you that example, if you say carbon nanotube is a rolled up graphene, carbon nanotube could be, okay, if you're looking at that, then the surface area of the graphene will be more than single carbon nanotube. But if you put several carbon nanotubes, a bundle of carbon nanotubes, I'm pretty sure Professor Shirsat is going to talk about things where he has several carbon nanotubes together. But lately we use a network of carbon nanotubes. We can get much higher surface area. But if you're trying to compare a single carbon nanotube versus a single layer, then most likely the 2D material has a higher surface area per unit volume compared to the single wall carbon nanotube or single carbon nanotube. So we have my goal originally when we first started working on nanomaterials was to work with single nanowires, because I always thought we wanted to do single molecule detection. And that would be only possible on a single nanowire, but it was too hard to work with single wires. I'm done with my answer. Is it satisfactory, or is there a follow-up question?
Yes, sir. There is no more question, sir.
Okay.
Okay. Thank you very much, Professor Mulchandani, for your wonderful talk. We'd like to listen to you even more. I don't know how to arrange that. This is excellent. With Tapan here, I think we can get some more ideas from you. There are more smarter people in US, but that's not really true for India. So we'll benefit from you and expect some help from you in terms of ideas. Thank you very much.
Thank you. Thank you all for listening to me. And I'm not sure whether I'll be able to hang on for too long. So because it is close to 11 o'clock. So I will try to do my best to last for another half an hour for Mahendra's talk.
Okay, no problem, no problem.
Because Mahendra was my postdoc and a visiting researcher twice. So he also has a training and a connection with UCR.
Yeah, okay. Let me introduce our next speaker, Professor Mahendra D. Shirsat. He is presently working as a professor in the Department of Physics, Director, Musa Center for Advanced Sensors Technology, Director, DTU Kaushal Kendra, and Head, Department of Electronics, Dr. Babasaheb Ambedkar, Marathwada, University, Aurangabad, India. He was postdoctoral fellow of Professor Mulchandani, as you have heard, and visiting scientist at the same department. He was visiting principal fellow at University of Wollongong, University, Australia in 2006. He was visiting professor at Hanyang University, South Korea in 2013, and National Taiwan University of Science and Technology, Taiwan in 2018 and 19. Professor Shirsat has 32 years of experience in teaching, research, and innovation. He's having around 9 years of administrative experience. He has 130 research publications in peer-reviewed journals. He has a very high H index of 31 and I index of 89. He has 8 patents in his credit. He has successfully supervised 18 PhD students and 5 postdoctoral scholars. He has undertaken 25 major research projects from various funding agencies in national level with a total grant of 17.12 crores. He has played vital roles to establish Deendayal Upadhyaya Kaushal Kendra, formerly Center of Vocational Education and Training, CVET, and Department of Electronics, and started BVOC, MVOC, and MSc to impart skill-based education in the area of industrial automation and automobile industry. Professor Shirsat has established Center for Advanced Sensor Technology for various development of sensors with state-of-the-art facilities in the area of material synthesis, characterization, and device fabrication. He played a pivotal role in the capacity of IQAC director during the third cycle of NAC accreditation of Dr. Babasaheb Ambedkar, Marathwada, University of Aurangabad to secure A grade. So is a wonderful combination of administrative and academic capabilities. Let's listen to him. So Professor Shirsat, the stage is for you.
Yes, thank you very much, Chairman Professor Datta, At the onset, let me thanks the organizers, particularly one of my very good friend, Professor Rajesh Kumar. And I would like to also thanks all the members of organizing committee, including HOD, Dean, and all faculty members of Department of Physics. Before I start proceeding, let me share my screen. I hope my screen is visible to everybody.
Can
yeah.
you get
Yeah.
full screen? Okay, thank you.
Is it okay, sir?
Yes, it is absolutely okay. Go ahead,
Okay.
sir.
Thank you very much, sir. Today I will be speaking on sensor array based on organic conducting polymers and porphyrin functionalized by SWRTs. Truly speaking, I am really fortunate that Professor Mulchandani has already, summarized what the chemiresistive and chemfet modalities of various sensing. And I will be exploring only two materials, three materials rather, single wall carbon nanotubes, and how, because there are certain advantages as well as some issues of single wall carbon nanotubes, and those issues can be addressed if you modify single wall carbon nanotubes by organic conducting polymers and porphyrins. So I'm going to tell you how the devices can be developed. To begin with, I would like to sincerely acknowledge all research scholars, my collaborators, and financial supporters. And particularly today, I would like to express my special thanks to my mentor, Professor Ashok Mulchandani, because I was with him under Bioscas Fellowship somewhere in 2007, and later on, he was kind enough to offer me NIH Fellowship, and I was there again with him for another 1 year. So today, whatever I'm going to present, it is like I got the rigorous training under his able guidance, and in fact, one of the objectives of that NIH Fellowship was the scientist or professor from the developing country should go there, earn some skills, and he should come back to his or her own country and try to implement those skills, right? So what I did when I came back to India, I try to, that's why I should express my sincere thanks to particularly DST. We have got substantial grants from DST as well as RUSA and many other funding agencies too, to install very state-of-the-art facilities in my university. So to begin with, I'm sure like I'm going to have only 30 minutes, and I will try my level best to finish everything within 30 minutes. But if I'm not able to do it, I will request the chairman to please tell me where should I stop, because I thought let me introduce my lab. I mean, the RUSA Center for Advanced Sensor Technology, and then I will be giving brief overview of what kind of materials can be utilized for chemiresistive and chemfed platform, and then I'm going to tell you like how these platforms can be developed, and then I will be summarizing. To begin with, I have decided to introduce my lab. The reason for that is before I went to US, because I mentioned as it is mentioned by the in my introduction that I spent good amount of time in like at UCR. To get access to the state-of-the-art facilities for material synthesis, development, and device fabrication as well. So what I did, like whatever funding I got from various funding agency, and fortunately in 2016, because I started getting funding since 2000, almost like 2000, but I got substantial funding from RUSA, and as a result of that, we could establish a RUSA Center for Advanced Sensor Technology in at my university. And this is some sort of common facility center having state of the art facilities in the area of material synthesis, characterization, and device fabrication. And whatever facilities I'm going to show you to begin with, these facilities are open to all research scholars across the country. So far we have initiated around 35 to 40 collaborative proposals, and I always make sure that whenever we are having collaboration, collaboration means like I always encourage the teachers, young faculty members from affiliated colleges, and particularly that's not only affiliated colleges, because in state universities also most of us are struggling like anything for having state of the art facilities for doing quality research in India. and therefore I do struggle a lot to begin with. So therefore what I did, we started inviting proposals from various affiliated colleges and state universities, and as a result of that, since 2016 we could have, as I and 30 accordingly we had a good number of Scopus index paper as well from those collaborators. This is the entrance view of my research laboratory, center. And there are, as I mentioned earlier, although we have got wonderful facilities for material synthesis and sensor, characterization and sensor device fabrication, our main focus has been, because this is a multi group we could create in my university, and we are having the professor from Department of Chemistry, Computer Science and Physics together, and this is a sort of interdisciplinary center we have established. And as far as my research group is concerned, we have a focus on developing materials for sensors which can detect gaseous element, particularly as it is mentioned by Professor Ashok, like we are more on VOCs detection and heavy metal ion detection. And similarly, it's not only laboratory level research, because I thought, like, since we spent enough time in the laboratory, now whatever, and since we got enough number of Scopus index papers, now we should move ahead, and we are focusing on development of prototype devices as well, and we have developed a few prototype devices as well. And one of the computer science group, they are working on remote sensing for analysis of surface materials and vegetation. As far as science and technology integration is concerned, in my center, we focus on basic research, and we always ensure that basic laboratory research will be converted into some sort of laboratory application to begin with, and then prototype. And since I'm also heading another center, the Deen Dayal Upadhyay Kaushal Kendra, as it is mentioned, like wherein we are running BHOG and AMOC industrial automation and automobile courses, we have got good connectivity with industry. As a result of that, we are helping people to have the technology transfer as well. We are not behind in the capacity building also, because through this center we are doing capacity building of UG student, PG student and research scholars. It's not only student but even for young faculty members also. We are regularly organizing the familiarization and awareness program for all those people, so that they can get aware of what kind of facilities we are having, and then we will tell them what would be the modus operandi, what would be the way by which the facilities can be utilized and they can do a quality research. This is the list of this is research impedance and the list of facilities what we have for material synthesis, material characterizations and device fabrication. I'm going to show you quickly the pictures. This is the pictures of the process laboratory which we have developed in the Rusa Center, because since we know that most of the chemicals are very hazardous in nature, we have to be very careful about the health of our research scholars who are going to work in the laboratory. And this is another view of process laboratory and the cubicles we have developed for the students, research student. And then we have a fabrication laboratory in which this is a CVD machine which we are using for synthesis of carbon nanotube. This is indigenously developed. One of the beauty of this machine is this is indigenously developed machine. This machine has been developed by our masters and post research student. And for growing 1D to 3-dimensional materials, we are working on organic conducting polymers more or less, like nanowires, and then surface modification of Cnts. So we are having couple of CH electrochemical workstation, and then we do have a westbound wire bonded machine for device because whenever we are coming up with the material testing in the laboratory, we need to test at devices as well. And then this is the probe station which we are having for alignment, because of course along with the 4200 Ketley and then CH electrochemical bus station, we can use probe station for alignment of carbon nanotubes. And we do work on the envelope material crystals as well. That is another area in which we had a good number of papers, like we are using low temperature solution growth method to grow envelope materials, and we have developed like couple of PhDs and good number of research paper as well, and many affiliated college teachers, they are using these facilities. This is another view of the fabrication lab. You can see this is Ketley 4200 semiconductor parameter analyzer I was talking about. We are using in conjunction with this probe station. And this is VSINIR hyperspectral imaging spectrometer, the computer science group we are using for surface vegetation. We do have a microsystem technology lab, clean room of 10,000 class, in which we have a SUS Microtech mask aligner for like for pattern generation. Like we started very recently, we started working on MEMS as well, but we don't have any significant data with us as on today. I mean, we most of the data is under publication. And then we have this EV and thermal evaporator in high vacuum, and then these are another view of the same laboratory. And then we do have a sophisticated characterization laboratory. We have X-ray diffractometer, D8 Bruker D8 Advanced, in which we can do one dimension. I mean, like powder. Like X-ray diffraction of powder, micro diffraction, liquid sample, and you can study pair distribution function as well. This is the kind of very advanced system we bought. And then we do have another characterization systems like AFM with STM, UV, FTIR, because once we synthesize material, we need to test it at next level so that we can see like whether whatever material you were expecting, whether you end up with the same material or not. And similarly, very recently we bought a Raman spectrometer, Horiba, and BET surface area analyzer. So this was the list of facilities which we are having as far as material synthesis, characterization, and device fabrications are concerned. As I mentioned earlier, we are also working on the handheld sensing gadgets. So far we have developed a couple of prototype devices as well. We already submit patent for this. This is the only detection of ammonia, and this is quadranulate sensing gadget. We have developed two different kind of sensing gadget of this kind. So this is for NS3, CO, SO2, and BTEX, and this is very, very cost effective sensing gadget, let me tell you, my friend. And as far as the capacity building is concerned, this is how the event calendar of my center is going to be. This is of course the last February, and since March onwards we stuck up with lockdown and we could not organize this kind of program later. Usually every month we organize familiarization workshop, then we call the proposals for short-term and long-term project. I mean, we are not funding, but like proposals for making use of the facilities. And then like we shortlist some of those, and we provide them hands-on training on the equipment what we are having. And then at the end we will be selecting those proposals, and then we will be working together. And then in order to create some sort of IP awareness, we always have the IPR workshop as well every month. So these are the kind of activities the center is organizing every month. And since, as I mentioned earlier, since last March we could not organize, so we are planning to have online. Some of the activities could be organized online as well, like familiarization workshop, IPR workshop as well. And this is the website of my university, wherein you can see the Rusa Center for Advanced Sensor Technology. You can click on there and you can go ahead and see what kind of facilities we are having. And if you don't want to use if you don't want to work with us in collaboration, then we are offering this facility on tariff basis as well. We have, since last 4 years, we have 4 to 5 years, we have earned lot of revenues also. This is the tariff card for all the facilities which we are having, and we are offering these services as well. Let me switch to the material overview. As far as material overview is concerned, you can see, as it is mentioned by Professor Ashok Mulchandani, there are many materials which are being explored for sensing application. And some of the most explored materials are porphyrins, carbon nanotube, graphene, metal oxide, phthalocyanine, organic conducting polymers. And then very recently we started working on the MOF as well, graphene and MOF as well. But whenever we are talking about the material like this, let me tell you, my friend, this presentation I have prepared specifically for the students and those faculty members who are going to start their research activities in the area of sensors, so that this presentation is going to be very useful for them, because I started from fundamental. Now, whenever we are talking about screening of material, we need to see like what are the advantages and what are the issues with that material which you will be using. So as I mentioned earlier, in our sensor platform, we are using carbon nanotube, single wall carbon nanotubes as a sensing backbone, right? And since we are using CNT as a sensing backbone, we need to understand what is going to be advantageous aspect and what are going to be the disadvantages aspect. As far as advantages concerned, since because of the nature, graphene, tabular nature of graphene, the carbon nanotube, the outer surface of CNTs is going to be very, very electrochemical active, and therefore whenever it going to be interacting with any gas analyte, it will be easier for the CNTs for having some kind of exchange of electron exchange, either accepting electrons or donating electrons to the analyte which is being exposed to the CNT. And another advantage aspect everybody knows, like, is it has got, since it is now one-dimensional nanomaterial, it has got one excellent surface to volume ratio, which is going to be very important as far as sensing application is concerned. And moreover, it has got a very excellent thermal, mechanical, and electrical properties as well. It can be used in any harsh condition. So these were some of the advantages aspect. Now, as far as the disadvantage, there are certain issues with CNT. If you are using CNT as a sensor, then there are certain disadvantages aspect as well. Like, one of the very serious problem with CNT could be it has got very poor recovery. Why? Because we know, like, CNT has got honeycomb structure, and whenever you are using bare pristine CNT for sensing application, the gas molecule may absorb in towards the at the inner side of the CNT, because they are going to percolate through those honeycomb structure. As a result of that, whenever we are talking about recovery, because as far as sensor is concerned, you need to have a good response as well as recovery time. But if you are using pristine CNT, then because of this honeycomb structure, you will be having lot of problem with the recovery of the sensor. Now, it also has the poor selectivity because due to limited transduction mechanism. Because as I mentioned earlier, yes, it has got although it is electrochemically active, but like, since it is since it is electrochemically active, by and large, with the most of the analyte, it is going to be is going to have some one or other interaction. As a result of that, it will be very difficult to inculcate selectivity if you are only using CNT, pristine CNT as a sensing backbone. And but however, there are certain VOCs wherein we have very poor response for CNT is responding very poorly. For those analytes is going to have very poor sensitivity as well. And most importantly, dearth of efficient methodologies for incorporation of CNTs in sensor matrix. So these are some of the issues you will be having if you are really working on CNT CNT material as a sensing backbone in your matrix. What are the conventional wayouts as far as recovery is concerned? You can expose your material to UV light. You can treat it for high temperature for 15 to 20 minutes. But unfortunately, if you're talking about laboratory research, yes, it is fine. But if you really want to have the devices, it is not going to be good. This approach is not going to be good for mobile sensing application. As far as selectivity is concerned, of course, you can decorate CNTs with various metal nanoparticles, because the metal nanoparticles are going to be good for inculcating selectivity, and it can be still like you can address this issue. But even if you are decorating CNTs with the metal nanoparticle, but still that honeycomb structure is going to be still exposed to the analyte, and then you are still going to have a recovery problem. Although you can address selectivity, but you will have still having selectivity, the recovery problem. What our approach is, because this approach we started adopting when I was in UCR with Professor Ashok Mulchandani, because I got rigorous training, as I mentioned earlier, by like aligning CNTs by using AC dielectrophoretic alignment. So you can use AC voltage. Of course, you need to optimize AC frequency, time, and then peak to peak voltage to align your CNTs. And I'm sure you cannot have one single CNTs as WNT bridging the gap, but you are going to have plenty of CNTs bridging the gap. And that is why, in that way, there are certain advantages if you are using CNTs in sensor or graphene. But graphene has its own inherent advantages if you are using graphene, because we started using graphene as well, and we got good result with graphene too. But today I will be focusing on CNTs. Then another approach with what we started adopting is functionalization of CNTs, covalent and non-covalent, by the various material to inculcate selectivity. Like, we are using organic conducting polymers, as I mentioned earlier, porphyrin, and then the top of organic conducting polymers still we can have, and then go ahead and then again further modify with metal nanoparticle. Not on bare, but like initially you will be having CNTs, and the top of that you can have the covering wonderful thin coating of organic conducting polymer or maybe porphyrin, particularly OCP, and then you can decorate that composite structure with metal nanoparticles. And the one of the advantage of this approach is you are going to wrap up CNTs with organic conductive polymer or porphyrin, and therefore that honeycomb structure is not going to be, truly speaking, that CNT is not going to be exposed to analyte. Rather, there will be some sort of electron exchange mechanism happening between your porphyrin or conducting polymer with CNTs, and then the top layer, like either organic conductive polymer or porphyrin, is going to speak with the analyte. So this is what the structure of our device is going to be. Now, what are the functionalizing entities? Like as I mentioned earlier, we are using the in this particular talk, I will be talking about organic conducting polymers and porphyrin. There are the reason for that is there are certain advantages because organic conducting polymers can be easily synthesized. Most importantly, the sensitivity can be, conductivity can be modulated significantly. And we know conducting polymers are not stable in bulk form, but like if you are synthesizing conducting polymer at nano level, you can enhance the stability as well. And obviously, they are good for inculcating selectivity also. I'm going to refer that. And then as far as porphyrins are concerned, relatively as compared to conducting polymers, porphyrins are more stable in the environment. They do not degrade under any ambient environmental conditions, and specificity can be rendered because you can have free base porphyrin or metal substituted porphyrin. I will be speaking more on this aspect whenever we will be moving further. Let me talk about some of the advantages aspect. Like let me extend a little bit. Like there are, as I mentioned earlier, polymers can be conductors, can be insulators, can be semiconductors, and like this is the first group. Like they first time they showed that yes, polyethylene can be conducting polymer. That first time they got Nobel Prize. So it can be synthesized by plenty of acid route. Modulate conductivity can be modulated, and most importantly, they can be used for conductometric, potentiometric, and amperometric transducer as whenever we are using as active layers in FETs. However, the conducting polymers also have some issues, right? That we need to take care, right? That is one of those issues. Are some of the issues are low electrochemical activities and hysteresis. Obviously, we need to address those issues as well if you really want to use a conducting polymers. And then whenever you are using conducting polymer, you need to understand whether this conducting polymer, like if you want to use conducting polymer as a coating layer, so then we need to understand whether there would be some sort of interaction between CNT and conducting polymer. So through literature, we came to know that we can have a wonderful intimate contact between CNTs, AWNTs, and conducting polymer through pi stacking. So this is going to be wonderful, and same thing is true with porphyrin as well. And another advantage is by changing the dopant, different electrolytes itself, the selectivity can be modulated. This is one of the very important advantage. And polymer does not allow analyte to get direct in contact because, as I mentioned earlier, we will be coating CNTs with organic conducting polymer. So the polymer would be the sensing layer, and underneath the CNT would be a transition layer underneath, as per the devices are concerned. The another the material which can be used for modification, surface modification of porphyrin could be surface modification of SWNTs rather could be porphyrin. What is porphyrin? The porphyrin molecule is usually described as union of 4 phosphorylic link by 4 methane bridges to form a microcyclic element. And let me tell you, my friend, these are some of the example of free base. You can have, as I mentioned earlier, you can have free base porphyrin or metal substituted porphyrin. There are certain advantages of free base as well, but if you really want to have like take the advantage, it would be always better to have a metal substitution. You can see this periodic table, all these green element can be substituted, can form a complex with the porphyrin, and then we can have the metalloporphyrin. And these are 2 examples of metalloporphyrin. You can see ruthenium acrylyl porphyrin. You can see the ruthenium is sitting at the center, and you can see the as far as the ethyl group is there, you can have the surface on the periphery, you have got the ethyl group. Now this is tetraphenyl porphyrin with zinc at the center. This is another porphyrin. You can see here zinc sitting at the center, and on the periphery you have got phenyl group. So whenever we are talking about interaction of these porphyrin, because we will be coating CNTs either by organic conducting polymer or porphyrin. So if you are coating CNTs with porphyrin, this porphyrin can have interaction with VOCs, your VOCs, right? So here the central metal as well as the periphery, that both of them, both the the components are going to be very going to play a very significant role as far as some sort of electron exchange mechanism is concerned. This is some of the list of porphyrins and probable analytes. These porphyrins are more shows more affinity towards this some of the analytes, VOCs rather. Now again, like whenever you, as I mentioned earlier, whenever you're talking about the surface modification of any material, you need to make sure that whatever material you will use, you will be using for surface modification, that is going to have some sort of interaction with the underneath layer. So same thing here, you can see the porphyrins are electron donor, and they also can have a intimate contact with CNTs through bypass taking, and they are metalloporphyrins in particular are wonderful electron donor system. And obviously as a result of that, for carbon nanotube as a p-type material can you will be able to modulate the conductance of underneath CNT level. And then moreover, whenever we are talking about interaction of metalloporphyrin with gas analyte, as I mentioned earlier, here the center metal as well as the peripheral group, that is going to play vital role whenever we are talking about the sensing mechanism. So what we essentially we are doing, we are using CNTs as a backbone of all the devices, and then we are modifying the devices with various porphyrins and organic conducting polymer. Now I'm going to quickly show you the camera resistive and chemical platform how we are doing. This is the platform which we are using this because I used to work on this platform when I was in UCR and Tapan, because the Tapan is also, we were working together. I remember I was postdoc and he was doing PhD during those days. So we were working together. We had one joint publication as well. So we had a very good time. I hope Tapan must be very happy to listen me. This is the platform which we used to use. Even still we are using that because we are fortunate to have still this platform with us. You can see here what is this platform is all about. We have got we can see we have got Si substrate, and the top of that SiO2 chromium layer, and this is the gold pattern I'm talking about. So here at the tip we are having 3 micron gap. So on this 1 centimeter by 1 centimeter square chip, we are having 16 devices. This is the sensor array I was talking about, and this 3 micron gap we are using with CNTs, right? And then as far as camera resistive is concerned, this SiO2 layer 300 nanometer could be no issue. But as far as the FET is concerned, we want this SiO2 to be around 100 nanometer, right? And then let me tell you, my friends, since we are having facilities with us, now we are come up with this. This is not a fully developed device. We are going to have this 8 electrode design now, because this is 16 electrode, which what we used to work on. Still we are using this, and now very recently we started using this as well, like 8 electrode device. Since we have clean room facility with us, now we can have this pattern with it. We started working on that. Now let me go ahead and tell you like what this platform is all about. You can see this is the gap we are having, and this gap we are going to bridge by CNT. As I mentioned earlier, CNT is going to backbone of all the devices, all 16 devices. And then what we are how we are doing this, because like whenever you are talking about CNT powder, you are going to have some contamination as well. So we need to do sonication and centrifugation so that all those contaminants can be removed and supernatant can be collected. You will be having very fine suspension of CNT. You can see the change in color difference, and then you have to put a small drop, maybe around 0.5 microliter on the top of this electrode, and then you have to apply AC signal. Of course, this AC signal frequency, as I mentioned earlier, frequency, time period, and peak-to-peak voltage need to be optimized so that the adequate number of CNTs could be produced. Otherwise, you will be having complete network. We don't want network of CNT. We want aligned CNTs so that you can have better transduction mechanism taking place whenever we are talking about devices. Obviously, there are certain device-to-device resistance variations also, because since we are having 16 devices on chip, and then we are aligning CNT one after other. So it is very challenging to have, because we used to struggle like anything, and still it's not easy rather. But if you are like working, like if you are used to with this kind of experimentation, then obviously you can to some extent you can optimize the parameter, and then device deviation in the device resistance is going to be minimum, because you don't want your device resistance to be deviated too much. Otherwise, the repeatability and reproducibility is going to be a great headache. For CNT processing, like we are using this small equipment for centrifugation and sonication. This is the experimental setup. As I mentioned earlier, we have developed in our laboratory. I was really, Professor Ashok, if he is online, he will be very happy to see that whatever instrument I used to I used to use in UCR, all those equipment I could procure in my research laboratory. It's not only me, like I made these facilities available to all the research scholars, those who are interested across the country, and there are many research scholars, they are making use of this facility as well. And this is FESM. This is, I don't have this FESM in my laboratory, but we have in the common facility, I mean in the university CIFART center. We are using that for like just to see like whether we got some, although you can see I'm sure like it may not be visible, but I will show you a couple of more figures. You can see here, this is our own AFM. We are having AFM with STM, as I told you earlier, and you can see here some of the CNTs bridging the gap. But you see, as I mentioned earlier, you cannot have single CNT bridging the gap. It's going to be bundle of CNTs and network of CNT. But we don't want cross network. We want align CNTs, right? And for that purpose, optimization is going to play a very important role. Because if you truly want to have, because at the end of the day, if you really want to have good sensor, then what is your response time and low detection limit is going to play very, very important. And this, like the total number of CNTs bridging the gap and how they are bridging, like whether they are online or cross network, that those factors are going to be decided by these, like CNT aligned CNTs. I mean, like if you really want to have a very lowest low detection limit and very less response time, you need to make sure that your CNTs are aligned. They should not be cross network CNTs. And then obviously you can see this is this is bundle of CNT, but you are going to have, it's not only single bundle you will be having, there will be more. But just for the sake of visibility, I have cut down those picture, and I thought let me show you how it looks like under FESM and AFM. And then you can go ahead, because once you align, you need to do several characterization. First, I have not mentioned here, but to begin with, you need to do IV, just to see like whether you got something aligned in your 3 micron gap. And then once you do IV, then you can go ahead and have like if you are having Raman with you, you can see those peaks, right? Whether it is going to be there or not. And then you can see the AFM and FESM if the facilities are available. Once we confirm that CNT, you have got all 16 devices and you bridge those 16 devices with CNT, then next step is you want to modify these CNTs with 2 different material, as I mentioned earlier, organic conducting polymer and porphyrin. Now, as far as organic conducting polymer is concerned, like modification of CNTs, that too in 3 micron gap. You see, gap is only 3 micron. And again, like the total device almost geometry is going to be 250 micron height of that, like the 3 micron gap. Although width is 3 micron and height will be 250 micron. And therefore, essentially, specifically, coating CNT is going to be one of the challenging aspects. And as far as the electrochemical, we are still using electrochemical polymerization, but this is going to be charge control potential static deposition, because you can terminate your potential static reaction on the basis of charge, because you can set under CH, there are many electrochemical workstation you can use, but in CH electrochemical workstation you have this facility. You set the charge, and then once the charge reaches, automatically the reaction is going to be completed, terminated. So you can see like we tested like right from 3 microcoulomb to like 100 up to 100 microcoulomb. We got different results, but unfortunately I'm not going to show all the results because the time is not going to allow me to do that. But I'm showing you how the devices can be developed, right? This is the circuit layout of the electrochemical setup. You can see this is we are going to have a wire counter electrode, similarly reference electrode, and those pads, gold pad, are going to be our working electrode. And this is how the circuit we are using. This is the experimental. You can see this is the chip we are using, those electrodes, and then this is the schematic diagram, and these are the actual working photographs which whenever we used to align the CNTs. And this is a CH electrochemical workstation we are using. Of course, we have got a couple of electrochemical workstation for this purpose. And then as far as the modification, you don't need to do anything. This is just a drop casting. You prepare porphyrin solution, drop cast it, and incubate it for specified time. Of course, that time incubation time need to be optimized. It should be right from several seconds to few minutes. That need to be optimized, so that you don't want complete coverage there. Also, you want specifically coating of porphyrin on CNTs. Of course, once you do that, you can do IV before modification. After modification, you can do IV. You can do SEM along with ADAX, like if it is like FeTPP, for example, this trace of Fe can be there, trace of Ru can be there, this metal trace can be detected through ADAX, and then you can confirm that yes, you got coating of the desired porphyry non-SWNT. This is how you have to do. So once you have aligned CNTs modified with organic conducting polymer or porphyrin, then you need to do, as I mentioned earlier, several characterization. To begin with, you can do IV and FET, because IV FET can tell you like what would be the change, because I know like even conducting polymer also do the same thing. They are donating most likely they are donating electron most of the conducting polymers and metal nanoparticles as well, metal porphyrin as well. And then you can see like before modification and after modification what would be IV. Similarly, the similar investigation can be done by FET. I mean the output characteristics as well as transconductance, and obviously CV also, because pristine CNT will have different CV. Electrochemical characteristic can be done and modified with porphyrin or modified with organic conducting polymer will reflect the different peaks, right? Is peak position and then height can be easily noticed. Then you can also do structural characterization like FESEM, XR. I'm talking about the XRD. XRD I have not mentioned here. XRD and morphological. You can do XRD, FESEM, IDAX, and AFM if this kind of facility is available with you. And obviously, you can also do some spectroscopic like UV, FPR, Raman to confirm that you have got surface modification, you have got CNT aligned in the gap, and then you modify that CNTs with desired material. Once it is done, you can see there's some of the example. I thought like, let me quote you. You can see here. This is SWT green IV reflect bare SWT pristine, and you can see TPP. This is like SWT modified with TPP. You can see the increasing resistance, right? And similarly, the similar changes you can observe in FET also. This is FET transconductance of FET of bare SWT with TPP tetraphenyl furfurin modified with SWT modified with TPP. You can see the significant difference not only in slope but as well as in threshold level also. So this is how, and then obviously you can do UV. Of course, there would be significant difference in UV of SWT. Then your this is cobalt octahedral porphyrin and modified CSWT modified with cobalt octahedral porphyrin. And then obviously you can do FTIR and then some spectroscopic characterization to see there is a significant difference, noticeable difference between surface model like pristine CNTs and modified CNTs. And then these are the AFM I have already mentioned. You can see this is bare SWT high profile, because if you are having the atomic force microscope with you, you can see the height distribution as well. This is bare and this is modified. And these are again some of the FESM images. And once you do this, then you can go ahead and do the semi-resistive or chemical characterization of the sensing. As far as sensing is concerned, this is schematic of chemi-resistive. You can see I don't have any gate here, only 2 electrode devices, and this is the most likely the chemi-resistive sensing graph, a very popular sensing graph you can have. And as far as the FET is concerned, we are using backgated FET. As far as the OC sensor is concerned, we are using backgated FET. For heavy metal ion, we are using liquid channel FET, gated FET. But here it is backgated FET because this gate itself can be considered as a gate. The silicon substrate, I mean to say, can be considered as a gate. And this is the schematic of backgated FET, and these are some of the examples. These are the actual results from one of our published paper. This is for this is in presence of air. Bare SWT and of course like porphyrin coated with SWT, and then this is for these dichloromethane, and this is for acetone. You can see the difference in slope as well as the threshold voltage as far as FET is concerned. Now, whenever we are talking about the mechanism, sensing mechanism, there are two different. I'm not going to stress too much, but quickly let me go through very quickly. There could be two probable mechanisms as far as FET sensing is concerned: Schottky barrier modulation and electrostatic gating effect. Schottky barrier means, like as it is mentioned by Professor Ashok Mulchandani, like here what we are doing, we are using gold pad, and on top of that we are aligning CNTs. So there will be like many a time there will be issue of contact resistance, and because of modulation in contact resistance, there will be some Schottky barrier modulation. So as a result of that, you can see there is a difference in slope. Threshold is going to be same, but slope is going to be different. But as far as electrostatic getting effect is concerned, here you can see the slope is same, but threshold is going to be different. In reality, we want both. Like if you are having both, then it means that in true sense you are having the FET device with you. And then this is how we are using, like once all the 16 devices are ready, we are putting it on the chip carrier. The same chip carrier, still I'm using Ashok. Even today we got it. We got the new chip carrier from develop similar chip carrier ready from our both Indian uh, vendor. And then we can do wire bonding by using Westbond wire bonding. This you can see, this is the Westbond wire bonder we are using. We have this wire bonder, and then this is the schematic of gas sensing setup. This is true dynamic sensing setup. Even in India, there are very few. Let me tell you, my friend, in India there are very few laboratory wherein the dynamic sensing is being carried out. Very few. And then this is the actual photograph of the sensing setup. This is completely indigenously developed by my group. This we are using for, as far as the dry air is concerned, we are using cylinder, but as far as the VOCs are concerned, we are diluting that in dental bag, and then we are testing. This is the closed look of the chamber which you are using. Here you can see very small chamber we have developed, wherein we are putting our device, and so that this is connected to the Ketley semiconductor parameter analyzer. So these are some of the research. I thought let me show you. In fact, characteristics of SWNT, TPP modified SWNT, and OEP modified SWNT. This is TPP modified. This is OEP modified. This is for, you can see, this is for SWNT TPP. This is, whenever we modify SWNT with TPP, this is for dry air, this is for acetic acid, and this is for benzene. You can see the substantial difference in the FET characteristic. The same thing is true with OEP as well. So, and then what is the overall, because I thought let me quickly show you some of the research, because I could not show you because of the time constraint, I could not show you the entire research. So this is the overall line of action in my laboratory as far as VOC sensors are concerned. So we have this sensor matrix on which we have got 16 devices. On the top of each device we have got 3 micron gap. This gap we are using by SWNT by using AC dielectroferritic alignment. And then once we have this aligned CNTs, then we can do electrochemical functionalization or by using drop casting. We can modify with either polymer or porphyrin, and then later also you can modify with metal nanoparticle if at all needed. This is for one device, and similarly we have to repeat for all the 16 devices. And then we can go ahead and do chemiresistive and ChemPET. This is the example of chemiresistive sensing, and this is the example of ChemPET sensing. These are actual result of some of our published data. And then once it is there, then we have to think of devices. So after this, because we used to when I was in UCR, we used to work up to this. When I came back, we started working on devices, and we come up with wonderful sensing gadgets as well. In summary, SWNT exhibit a very excellent thermal, mechanical, and electrical properties, and ensure well-defined pathway for charge carrier during signal transaction. And OCP and porphyrin, they are going to be wonderful material for surface modification, so that you will be able to inculcate selectivity, and whatever the issues I talked about right in the beginning, issues of like carbon nanotube, those issues you will be able to some extent, because all issues, because there won't be anybody across the globe that he will be claiming that he can address all the issues, but some of the issues which I have quoted could be easily addressed. So with this, I once again thanks organizer for providing me this opportunity to share some of the findings, and you have given me opportunity to make presentation. I don't know whether Ashok is there still, so I will be very today I feel very happy to present in front of my mentor, and I'm sure he will be very happy. And thanks to all the participants of this webinar for your patient listening. Now the control is handed over to the organizer. Thank you very much.
Thank you, Professor Shirsat, for your wonderful presentation. It's a plethora of carbon nanotube, single wall carbon nanotube, its functionalization by conducting polymer and porphyrin and metal induced porphyrin, and then its application and sensing. And you also introduced your centers very, very well. I'm sure some of our faculties and students will be very interested to write projects for you. So you are going to get some proposals from us. We expect some help. Your center is very well developed. And now I think there will be some questions.
Yes.
I'll ask the student coordinator to take it up. Vishnu, are you there?
Sir. Yes, sir. We have a question from Vaishali, Professor Vaishali Singh. Why
Yes.
is the CNT platform required? Can't we have freestanding films of metal porphyria?
You see, like because I still remember, but freestanding because there is no, because earlier also when Ashok was there, somebody asked like whether these aligned nanowires are going to play any role as far as sensing is concerned. Let me tell you, my friend, if you are talking about the three-dimension application, because it all depends on what kind of application you are doing, right? Because as far as the field emission application is concerned, then whether it is aligned or connected is going to make any difference. But as far as sensor is concerned, there are two important aspects. One is surface to volume ratio, right? Whatever the geometry you are using, whatever material you are using, you need to ensure that whether it is going to provide you enhanced surface to volume ratio. Then number one, and number two, whether you could engineer the band gap, because that material need to be in semiconducting region. Unless you have that material, let us say you have CNT, but if it is metallic CNT, that is why you end up, if you see the research papers, you will find very few research paper based on like multiple single nanotubes, right? The reason is multiple nano carbon nanotubes are going to be most likely metallic, right? And as far as single wall carbon nanotube is concerned, again it is very challenging, because when I was in UCR, there was one postdoc fellow from South Korea. He used to burn, because even in CSWNT, whenever you are aligning CNT, there, because you don't, even if you are growing or whether you are buying from any company, nobody can ensure you that you are going to have 100% semiconducting SWNT, right? So whenever you are having metallic, you need to get rid of those metallic, right? Either by burning. So we used to do that. One of the postdoc fellow, he used to do that, but somehow he did some experiment, got some publication as well. But success rate was very poor in that case also. So my question is, whenever whatever structure, whatever material you are using, you, as far as sensor application is concerned, you need to see like which application you are using, right? And what kind of properties, characteristics of material is going to be useful for your sensing application. By looking into that, you should choose the application, material.
There is another question from Archer. How does the sensor compare with several mesoporous metal oxide sensors with volatile organic compounds?
See, all metal oxide sensors are high temperature operation. Because whatever sensor I talked about, these are all room temperature operation sensor. Because nowadays I know you can provide heater, micro heaters are always there, but still, you need to have additional element there, right? So one of the disadvantage, I know like metal oxides are highly stable material as far as sensor is concerned, but one of the major disadvantage of metal oxide sensors are is rather the high temperature operation. So that you can get rid of that if you are using CNTs and all other materials which I talked about.
We have one more question from JR Ansari. What would be the impact on the efficiency if CNT, SWNT be replaced by 2D materials or quantum dots?
That's why I said, whatever material you are talking about, whether what kind of enhancement you have got. If let us say, like you are using like quantum dots, and if you are having, obviously it's going to have, because quantum dot is going to be zero-dimensional material, right? So in that case, you can have further enhancement in your surface area. But so now how you are going to align, that is also equally important. Like how you are going to use that quantum dots, right? So if you are not going to be, if using quantum dot is not going to be advantage as a device as a whole, because at the end of the day, you need to check, you need to see the performance of your device. Although on paper, it could be, yes, on paper, you will find that there is enhancement in surface area, but in reality, you need to check the device performance. And then only you need to decide what material should be utilized for enhancement of sensitivity, all those parameters.
We have one question from Lomas Rishi. Can these CNT survive in saline environment?
Yes, it can survive. And I don't think there would be any problem as such.
Now there is no more question, sir.
Thank you very much for your wonderful support.
Thank you, Professor, for your wonderful presentation. Would like to have some collaborations with you.
Definitely, I will be very happy. I will be very
For
happy.
your time.
Thank you. Thank you very much.
So we'll go for the next talk, and that will be from Professor Absar Ahmad, Director, Interdisciplinary Nanotechnology Center, AMU Aligarh. Professor Absar Ahmad, I hope he is there. Absar Ahmad has made pioneering and key contribution to the field of bio-nano science and technology, which have received high international acclaim amongst peers. Most notably, his entire volume of work has been developed and done in India, for which we can be proud. His work is noteworthy for its content of innovation and discovery based on imagination, keen observation, and application. It has an underlying theme of imaginative implementation of environmentally friendly green chemistry, room temperature biological and bio-inspired methods to emerging areas of modern science with multidisciplinary application. In particular, his works on bio-inspired synthesis of metal, semiconductor, and oxide nanosystems using fungal and plant extract media and related studies on the works on anti-cancerous drug extraction from endophytic fungi and their immobilization on nanosystems for drug delivery applications are expected to have significant impact on emerging field of nanomedicine. He has co-authored many papers in high-impact journals and has obtained a number of national and international patents. Professor Absar has been conferred with several prestigious awards, which include DBT Tata Innovation Fellowship, Ministry of Science and Technology, Government of India, New Delhi, Buswick Industrial Award, Material Research Society of India, MRSI Metal, CSIR National Chemical Laboratory Scientist of the Year, etc., to name a few. He has total peer-reviewed research paper of the number of 108. He has more than 22,000 citation, and his H index is 50. He has 11 international patent filed and granted, 11 Indian patent filed and granted. He has written 12 book chapters, and he has presented more than 170 international and national conferences and symposiums. Professor Absar, the stage is for you.
Thank you so much, sir, for nice introduction. First, I would like to thank the organizers for giving me this opportunity to share some of our work which we are doing on nanoscience and nanotechnology for the last 20 years. And I would like to thank Dr. Rajesh. He's also from Aligarh, for inviting me for this very important symposium. I am going to talk on biofabrication of inorganic nanomaterials and their multidisciplinary applications. Having spent 23 years at CSIR Pune, I was invited by the Executive Council of AMU to help in establishing a world-class center of excellence in nanotechnology at the esteemed Aligarh Muslim University. In view of the student welfare and knowledge propagation, I accepted the offer and joined AMU in December 2016 as the founder director of Interdisciplinary Nanotechnology Center. For the last 20 years, our group is mainly working on biosynthesis of nanomaterials using endophytic fungi, drugs from endophytic fungi, and recently we started the conjugation of drug to nanomaterials for targeted drug delivery. What are endophytic fungi? They live inside the plant. They are not toxic. They are safe. Daily we eat vegetables and fruit. They are full of endophytic fungi, but they don't cause any harm. Therefore, we have used endophytic fungi for the synthesis of a range of metal nanoparticle, bimetal nanoparticle, quantum dots, oxides, sulfide, porous carbon, graphene, graphite, biominerals, etc. We are the pioneering contributor to the field and have received high international acclaims amongst peers. Another very important area is drug from endophytic fungi. Taxol is a very important anti-cancer drug that is very effective for the treatment of breast cancer and ovarian cancer. But till today, we are isolating the Taxol from this plant. The name of the plant is Taxus baccata. It grows mainly in Srinagar and it takes 100 years to grow. And if you will harvest 100 years old plant, then you will get only 2 grams of the drug that is sufficient to treat only one patient. In order to provide the drug at low cost to the patients and no cost to the environment, I went to Srinagar and brought stem leaves of this plant, isolated 40 fungi and one fungus is producing Taxol. And recently we started the conjugation of drug to nanomaterials for targeted drug delivery. We have synthesized a range of nanomaterials in our lab, and now we are screening our nanomaterials in healthcare, agriculture, energy, environment, water, and so on. We are getting very good results. We are isolating a range of nanomaterials from endophytic fungi, not from actinomycete, not from saprophytic fungi, not from passive fungi. And recently we isolated a range of nanomaterials and drugs from mushroom also. Scuff fungi, yellow fungi, brown fungi, they are edible mushroom and they are not toxic, they are safe. And recently we are isolated a few nanomaterials from the truffles. These are the underground fungi. The cost is very high, very tasty, and India, nobody has started any work. And now we have isolated a range of nanomaterial from the poisonous mushroom. We have isolated a range of oxide, sulfide from the poisonous mushroom also. But most of the nanomaterials we are isolating from the endophytic fungi. This is Vinca rosea plant. We isolated several fungi from the Vinca rosea plant, and from the leaves we are isolating wind blasted vincristine, very important material for chemotherapy. But now instead of leaves, we can isolate the same drug from the fungus also. How you will isolate the endophytic fungi? This is very simple. This is the Vinca rosea plant. And now, how you will isolate fungi? Just take the leaves and wash the leaves with water and finally with mercury chloride and put the pieces on the potato dextrose agar. These are leaf pieces of Vinca rosea plant. The leaf pieces of Catharinthus roseus or Vinca rosea plant showing the emergence of endophytic fungi after 3 weeks. So we have isolated a range of nanomaterials from these fungi which we isolated from Vinca rosea plant. We have isolated a range of drugs from endophytic fungi, and similarly we have isolated a range of nanomaterials. Now I am going to skip this slide because everybody knows what is nanoscience and nanotechnology. This chemistry changes with this side. This is bulk gold, which is yellow in color, and chemically it is inert. But the moment you will change the bulk into nano, it becomes very, very reactive. And this nano is very, very important in advanced material, catalysis, and in biotechnology. And nano sizing causes changes in color, conductivity, melting point, light absorption, and so on. These are the gold nanoparticles. Gold is yellow in color, but these gold nanoparticles of different sizes are showing different color. Similarly, silver nanoparticles of different sizes are showing different color. And CDSC nanoparticles of different sizes are showing different color. Nanomaterials can be obtained by 2 methods, top down and bottom up. I think I can skip this slide. Now I will come to application of nanomaterial. Now, with the help of nanomaterial, we can target the doxorubicin. Doxorubicin is a very important drug for the liver cancer. But the problem is that The moment it goes to patient, it goes to liver, heart, and kidney. People are getting renotoxicity and cardiotoxicity. So now, with the help of nanomaterial, we can target the doxorubicin to liver cancer only. We know the liver cancer overexpresses a protein. The name of the protein is asialoglycoprotein. So in our lab, we made the target molecule which recognizes the receptor on the cancer. What we did, we synthesized anisotropic or isotropic gold nanoparticle. We attacked the doxorubicin, then we attacked the target molecule. The name of the target molecule is lectin. And now we injected into the penile vein of the rabbit, and you can see the whole complex will come and bind to receptor on the cancer. So now we can treat the cancer with the help of doxorubicin, as well as we can heat the nanomaterial. This is known as hyperthermia of the cancer. And now these are the other application of nanomaterials. And with the help of nanomaterials, we can improve the growth of the plant. And similarly, we can transform the cerium oxide in cerium phosphate. Otherwise, it's very difficult to convert the cerium oxide into cerium phosphate. But Pence et al., he used very simple method. He took the whole plant and converted the cerium oxide into cerium phosphate. And similarly, one can transfer the DNA into the plant cell, and now one can deliver the DNA into the plant cell. And this is very, very important. Like Wang et al., he made silica nanomaterial, and then because silica nanoparticle he made positive charge, and they attacked the negative charge DNA, and they injected into the plant cell, and they can deliver the DNA as well as chemical. We can make we can enhance the growth of the plant with the help of this method. And similarly, Maria et al., she used activated carbon, graphene, multi-walled carbon nanotube, single-walled carbon nanotube, and she saw the effect on the tomato plant. And finally, she reported multi-walled carbon nanotube enhances the growth of the tomato plant. And similarly, you can see the nanoparticle of gadolinium oxide can enhance the growth of the plant. This is control plant, this is treated plant. And similarly, you can see how we can control. This is the infected plant, and how we have controlled this plant with the help of silver nanoparticle. Big companies are working on nanoscience and nanotechnology. And if you are going to work on nanoscience and nanotechnology, you have to make nanomaterials. Nanomaterials can be obtained by three methods: chemical method, physical method, biological method. I am going to concentrate my talk only on the biological synthesis of nanomaterial. These are the nanotechnology is very, very easy. And you require several instruments for the characterization of the nanomaterial. And fortunately, we are very lucky. We have all the instruments for the characterization of the nanomaterials at Aligarh Muslim University. This is PM is very, very important. With the help of PM, we can see the shape, size, particle size distribution, core shell, or alloy, or you can check the crystallinity with the help of TM, and you will get the chemical composition of the nanomaterial with the help of TM. This is very, very important. And now, why biosensitive approach to nanomaterials? Nanomaterials can be obtained by physical and chemical methods. These methods are hazardous, eco-friendly, cumbersome, and yield big particles. Therefore, there is a growing need for reliable and economic synthesis of nanomaterial. We isolated a range of fungi, endophytic fungi, and actinomycetes for the metal salt reduction. This fungus we isolated from the Texas papata plant, this fungus from Vinegar rosea plant, and these microorganisms convert cyclohexanone to cyclohexanol. This is reduction reaction, and cyclohexanone to caprolactone. This is oxidation reaction. All the nanoparticle work, all the citation, so many publication I got on the basis of reaction. I thought, when the fungus can reduce organic compound, why not inorganic compound? So instead of cyclohexanone, I took silver nitrate. Fungus converted silver nitrate into silver nanoparticle, and gold chloride into gold nanoparticles. Nanoparticles which we are making from the fungus and plant, they are protein cap, they are water dispersible, shelf life is very high, they don't flocculate. If you will see, after 1 year, you will get 10 nanometer only. And now we can selectively isolate silica, titania, zirconia from any substrate, we can make monodisperse nanoparticle and we can make different shape and size of the nanomaterial with the help of endophytic fungi. Now I will come to intracellular biosynthesis of gold nanoparticle. The fungus, left-hand side is growing in water. Here the fungus is growing in gold solution. Initially it was yellow in color. Now the biomass in reaction class is changed from white to purple color or ruby red color, which clearly indicates the formation of gold nanoparticle intracellularly. If you will filter the flask, filtrate is colorless and biomass is colored. Now this colored biomass I calcine calcined at high temperature, and finally we got carbon supported gold nanoparticle, chemically, physically very, very difficult. And if you want to see the exact location of nanoparticle, you have to make ultra-thin section. We made ultra-thin section with the help of ultramicroscope, and finally we see under the TM, this is single fungal cell. You can see how the nanoparticles are growing in the fungal cell. And now we know the mechanism, but time is very short. I will explain the mechanism also. And now I will come to extracellular gold nanoparticle. Again, this very simple method. This is fungus growing in water, and here the fungus is growing in gold solution. Initially, it was yellow in color. Now the color of the biomass in reaction class is changed from white to ruby red color, which clearly indicates the formation of gold nanoparticle. In order to see whether the particles are extracellular or intracellular, we filtered both the flasks. Upon filtration, filtration, the filtrate of the control flash was colorless, and upon filtration, aqueous solution of the treated flash showed ruby red color, which clearly indicates the formation of gold nanoparticle extracellularly. And this is clear micrograph of the drop coated film of gold nanoparticles synthesized extracellularly. You can see all the nanoparticles are uniform in size, chemically, physically very difficult to make in such type of nanoparticle. And now these nanoparticles I tested on the cancer cell line, normal cell line, they are safe. And in order to see whether the nanoparticles are going to liver or not, then we radio-labeled these nanoparticles, injected it with the rat to see the biodistribution. These nanoparticles are going to liver and going to liver, kidney, and passing from the urine. And this is the gamma scintigraphic image of the gold nanoparticle in red. And these nanoparticles are passing from the urine because most of the nanoparticles which we are making in our lab, I keep the size 20 to 50 nanometer because our kidney can filter up to 50 nanometer. The nanoparticle will deliver the drug and they will pass out from the urine also. And now now we know the mechanism. Now we have isolated now that how the fungus convert the gold into gold nanoparticle and silver into silver nanoparticle. Now we worked very hard. After 8 years, we got the mechanism. We have isolated the enzyme and capping proteins. Suppose you want to make the gold nanoparticle, take gold solution, add this enzyme, add this capping protein, and you will get 5 nanometer. If you will not add this capping protein, you will get 100 nanometer. This paper we have published in RSC Advances. So now we know the mechanism how the fungus convert the cadmium sulfate into cadmium sulfide nanoparticle. And if time is very short, otherwise now silver nanopart, again we did a very simple reaction. The fungus is growing in water. The fungus is growing in silver nitrate solution. You can see the fungus converted the silver nitrate into silver nanoparticle. Now you will filter, you will get the brown color. This is PM micrograph of this one. And these nanoparticles are giving very good anti-fungal activity against Aspergillus niger. And similarly, we have isolated a range of nanoparticles and drugs from the edible mushroom. These mushrooms we collected from the Himachal Pradesh. Dr. Lakhanpal is the authority on that. He supplied all the mushroom, and we made a range of nanoparticles using mushroom. These are edible mushroom. This is a mushroom. Just we made the extract of this one. This is gold solution and mushroom. The moment I added mushroom extract converted the gold into gold nanoparticle. We have completely characterized. You can see this mushroom. I have not seen such type of synthesis. You can see the full grid is full of the gold nanoparticle. Chemically, physically, very difficult to make such type of nanoparticle. And another mushroom, Boletus isotope, again reacted with the fungus and again reacted with the gold. this voltage converted the gold into gold nanoparticle. You can see from 5 nanometer to 40 nanometer. Now, how you will separate these nanoparticles? This is a major issue. We are working in that direction also. Now, another mushroom. You see, this mushroom converted the gold into gold nanoparticle and silver nitrate into silver nanoparticle. Similarly, from Ganoderma, again we synthesize silver and gold nanoparticle. Here we are getting different shape and size of the nanoparticle. Chemically, physically, very, very difficult. And now after that, I move to algae also. Algae, everybody knows this algae I collected from the sea. And this algae converted the gold into gold nanoparticle, but they are intracellular. This paper I have in material science. And similarly, I have synthesized a range of extracellular gold nanoparticles from the algae. And now I will come to alloy nanoparticles. Alloy gold, silver alloy is chemically very, very difficult. I developed a very simple method. I took gold solution and silver nitrate solution, reacted with the fungus, and fungus converted the gold solution and silver nitrate solution into alloy nanoparticles. You can see we developed a very simple method. You know that I took only chloroauric acid, silver nitrate, reacted with the fungus, and now kept the flask for 24 hours. After 24 hours, you can see we got only less purple color, dark purple color, and finally we got brown color. The gradual change of color from purple to dark brown is the clear indicative of the formation of bimetallic alloy nanoparticle. And gold nanoparticle gives the absorbance at 5 to 550 nanometer, and silver nanoparticle gives the absorbance at 4 to 450 nanometer. The gradual decrease in UV from 543 to 443 is a clear indicative of the formation of alloy nanoparticle. And then I will come to platinum nanoparticle. Again, I know the as a microbiologist, I know the fungus which is oxidation, reduction, and methylation and so on. Like I took chlorophyllenic acid and I took the fungus which is reduction. And now fungus converted the chlorophyllenic acid into platinum nanoparticle. They are very important for the cancer and all. We have completely characterized, and this paper we have collided and surfaces, the interfaces. And then cadmium sulfate nanoparticle, sulfide nanoparticle is very difficult. We developed a very simple method. We took only cadmium sulfate and reacted with the fungus, and fungus converted the cadmium sulfate into cadmium sulfide nanoparticle. This is TM micrograph of the cadmium sulfide nanoparticle. And this paper, this paper we have published in JACS, because now we know the mechanism how the fungus convert the cadmium sulfate into cadmium sulfide nanoparticle up to 5 nanoparticle. They are highly fluorescent in nature, very important for the diagnostics and SAR. And then I made CDT nanoparticle. Again, I did a very simple reaction. I took cadmium chloride and tellurium chloride, reacted with the fungus, and fungus converted the cadmium chloride and tellurium chloride into CDT nanoparticle. They are highly fluorescent in nature, and they are very effective for the treatment of gram-negative bacterium and gram-positive bacterium and gram-negative bacterium. So they are giving very good antimicrobial activity. Then I will go to copper aluminum oxide. This is very important material for the diagnostics, very important material for some advanced material catalysts and so on. Copper aluminum oxide nanoparticle, chemically people are making at 1100 degrees centigrade under inner condition. It takes 4 days. I did a very simple method. I took only copper nitrate 1 millimolar, aluminum nitrate 1 millimolar, reacted with 20 gram of the fungus, and you will not believe the fungus converted this precursor into copper aluminum oxide. Very simple method I did, and this paper we have published in Advanced Material, the High Impact Factor Journal. This is TM micrograph of the copper aluminum oxide nanomaterials. They are highly fluorescent in nature, and now we know the mechanism, how the fungus convert this precursor into copper aluminum oxide nanomaterial. A range of silica, titania, zirconia, magnesium, barium, everything I made from the fungus. Barium titanate chemically people are making at 1800 degrees centigrade, but I have made room temperature. This paper we have in that. And after that, a range of biomineral I made from the fungus. Calcium carbonate, calcium carbonate, they are important material. We did a very simple method. We took calcium chloride, and the moment you will take calcium chloride, it will form calcium ion plus chloride ion. These calcium ions just find with protein secreted by the fungus and forms calcium protein complex. And finally, carbon dioxide exhaled from the fungus reacts with calcium protein complex and forms the calcium carbonate. we have series of publication, JAX, and one they can be Langur, etc. And now we have synthesized a range of calcium carbonate from the fungus. We have completely characterized the extraction carbonate from the fungus, barium carbonate from the fungus, and we have several publications in reputed journals. And similarly, I took the germinating seeds and reacted with the calcium chloride. Germinating seeds also convert the calcium chloride into calcium carbonate because germinating seeds also secrete proteins and exhale the carbon dioxide. I took the advantage of this feature and synthesized a range of biomineral using plant and endophytic fungi. And now lead toxicities and cadmium toxicities are very, very common in the drinking water. I took cadmium chloride and fungus converted the cadmium chloride into cadmium carbonate. And again, I took lead nitrate, fungus converted the lead nitrate into lead carbonate. So we can convert the toxic water into non-toxic form and directly we can use in the drinking water. And now we have synthesized a range of porous carbon from the fungus. This fungus material I took and then calcined this one. We got porous carbon size around 2 to 10 nanometer. We have completely characterized. Our idea is that if you this is a porous carbon 2 to 5 nanometer I made from the fungus. Our idea is that if you will take seawater, then directly you can convert the seawater into potable water because size is 2 to 5 nanometer. It will not allow the virus, fungus, bacteria, heavy metals, and bacteria, and so many microorganisms. Our idea is that I gave this material to some company. They are making the filter for us. If we will get the filter, if really our porous material will convert the our this material can convert the seawater into potable water, it will be a major breakthrough. And similarly, I made a range of porous carbon, graphene quantum dot, titania, for the energy storage and energy conversion. Recently, I made carbon supported platinum. The cost is 1 lakh 50 gram per gram, and that is very important material for the future. And since I did a very simple reaction, I took a fungus, I took chloroplatinic acid, fungus converted the chloroplatinic acid into platinum nanomaterial. Then we calcined that one. We got this figure you can see. We got carbon supported platinum, very, very important for the future. And similarly, silica is a very important material. I tried silica from the white sand, silicone sand, and from the rice husk. So the rice husk, if you will pluck any rice leaf or sugar cane leaf, you may cut your finger. This cut is because of this amorphous silica. What I did, I took this amorphous, sugar cane leaf or the rice husk, reacted with the fungus. Fungus first leaches amorphous silica into water, then convert amorphous silica into crystalline silica. This paper we have published in JAX in 2016. Similarly, white sand. You know, silica is a very, very important material. Till today, we are getting silica from USA, Japan. If you will give the order, you will get after 6 months. I was very, very upset. Then I thought how we can isolate the silica from the material. I came to know about the sand. Sand is made up of so many oxides. You know that just in 2006, I was in Pune. I took my scooter and went here and there in order to collect the sand. I could not get the sand. I am from Lucknow. I came to Lucknow after 2 days. I collected the sand from the river Gumti, and now this sand reacted with the fungus. Fungus converted this into silica.
Sir, I want you to converge within 5 minutes. We are spilling out of time.
Okay, sir. Okay,
I'm very sorry for this.
No problem. No problem. So now similarly, you can see I took titania. The titania cost is 300 rupees, and this titania is from the market and converted into nano titania, and here the cost is around 50,000 rupees. So we can convert the bulk into nano with the help of fungus. And similarly, lemongrass, I did my PhD on that. I made lemongrass extract. This is good solution, and we did a very simple reaction. We took lemongrass extract, and this extract we just added into gold solution. The lemongrass extract converted the gold solution into gold nanoparticle and silver into silver nanoparticle. This is TM micrograph of this one. This paper we have in Nature Material. The citation has crossed around 1700. And this gold is very, very important because they give the absorbance at NIR region. So they are very, very important for the hyperthermia of the cancer. And similarly, this nanoparticle I have made, this is very important for the MRI contrast, CT contrast, and this is the biodistribution of this one. Similarly, I made cerium oxide nanoparticle. We developed the disease in rat, and finally, we are trying to control with the help of cerium oxide nanomaterial. Our nanoparticles are giving very good anti-diabetic activity, anti-malarial activity, and now this nanoparticle I made from the fungus. This fungus, it is giving 81% inhibition against HIV. Similarly, I am going to test these nanoparticles for the COVID also, because these nanoparticles are inhibiting 81% HIV inhibition. And these nanoparticles which I made from the lemongrass, because they are not inhibiting or not giving any antiviral activity. But here, these nanoparticles up to 50 nanometer are giving very good anti-HIV activity. 81% inhibition we are giving. And now we are trying to just do some work on the COVID also. Now, this nanoparticle I made from the lemongrass, they can dissolve the cholesterol because they absorb the heat. And now we can enhance the angiogenesis, development of new blood vessels with the help of nanomaterial. And these nanoparticles inhibit anti-cancer activity. When the cancer is in every part of the body, it is very, very difficult to control. Now, our nanoparticles, you can see, inhibit the cancer cell migration also. And now our idea is that we have made a range of nanomaterial which are giving anti-diabetic activity, anti-malarial activity, and again, very important for the diagnostic, anti-HIV activity, anti-cancer activity, and so on. And now, already we published several papers, citation is very high. Now the time has come to just convert our basic science into process, product, and technology in order to translate all of the above socio-friendly research into usable product in the near future. The expertise, infrastructure, facilities available at AMU may play a prime role in that. Once a successful collaboration is established, we will together be able to introduce these valuable products, process, and services to the masses at a very affordable price and in abundance. With this, I conclude my talk. Again, I thank to Dr. Rajesh, he is our colleague from Aligarh Muslim University, for giving me this opportunity to share our work which we are doing at Aligarh Muslim University. Thank you very much.
Thank you, sir. Thank you for your wonderful talk. I'm sorry for the time restriction that we have. And you really used the nature, how to help the nature using fungi to prepare various kind of nanomaterials which can be applied once again in biological systems for cancer, for diabetes, even for COVID detection possibilities. So this is a wonderful arena where people can play. I'm sure this is an eye-opener for our colleagues, our faculty and the students, and I'm sure they can approach you and use your facility. Yeah, I'm really grateful that you spend your time, valuable time with us for this presentation. Thank you very much. Vishnu, is there any question?
Yes, sir. Yes, sir. There are two questions. One is from Maria from South Africa. She is asking if modeling studies have been explored and compared to experimental results. If so, how was the outcomes?
Hello. Yeah, please. Yeah, hello.
Yes, sir. I am repeating the question.
Yes, yes.
That this question is from Maria. She is asking if modeling studies have been explored and compared to experimental results. So if it is how?
Well, several people took the our expertise is to make nanomaterials. Like so many people approached us and they took our nanomaterials like oxide, sulfide, metal. They are interested in such type of things. But till today, I have not received anything. I already supplied the nanomaterials to so many people. But still modeling, I have not compared that one. I think the result, I may get the result very soon, then I can share.
There is another question from Dr. Karthik. What are the possible mechanisms? One second. What are the possible mechanisms involved in the antibacterial and anti-cancer activities?
Like antibacterial production of ROS. These nanoparticles enhances the production of ROS, reactive oxygen species. Till today, we have just we noticed this one. On the basis of that, we could prove our nanoparticles are giving very good antifungal, antibacterial activity. And similarly, cancer, so many things are DNA repairing, so many things are there. But still, we have not published full paper, or still we have not we are working in that area. We are collaborating with Dr. Kundu. He's from National Center for Cell Sciences. He told us, sir, we are getting very good anti-cancer activity. So that is because of the nanoparticles go and bind to DNA, because of DNA binding and because of some disruption in the DNA and all. And antimicrobial activity because of the production of ROS.
There is last question, sir. That is from Tanmay Bhatt. How were you inspired to use the lemongrass extract for nanoparticle synthesis? Is synthesis very common using natural means?
Actually, first we isolated a fungus from the lemon. I'm a microbiologist. First we isolated a fungus from lemongrass. That fungus gave me triangular nanoparticle. Then we thought, because fungus takes 4 to 5 days to grow, then you have to maintain at least 10 days. 10 days you have to give in order to get the fungus. Then you take the gold solution. You can convert the gold into gold nanoparticle. Then I thought, can we isolate gold nanoparticle in a second? Then we developed this method. Here I'm very happy. Just I made the lemongrass extract, added into the gold solution, and lemongrass extract converted the gold solution into gold nanoparticle within 30 seconds. Fastest methods we developed. That's why this paper we published in Nature Material. Very fast.
Okay, thank you, sir. There is no more questions.
Thank you very much, Professor. We are really grateful to you, and I'm sorry for the time constraint.
No problem.
Okay, we'll be going for our last talk by Professor Neeraj Khare. Professor Neeraj Khare is currently professor in physics department at Delhi. He received his PhD physics from BHU in 1986 and MSc in physics from Allahabad University. After PhD, he visited Department of Chemical Physics Application Polytechnic of Milan, Italy as an ICTP fellow during 1988. Subsequently, he joined National Physics Laboratory, New Delhi in Superconductivity Group as scientist in December 1983. He joined IIT Delhi in physics department in 2005. He has various visiting positions at Department of Material Science and Metallurgy, University of Cambridge, UK, IBM T.J. Watson Research Center, Yorktown Heights, New York, USA, Department of Physics and Applied Physics, University of Strathclyde, Glasgow, UK, Department of Inorganic Chemistry, Novosibirsk, Russia, Pohang University, South Korea, National University of Singapore. Professor Khare is internationally known for his research contribution in the area of superconductivity and nanostructured materials. He has published over 200 research papers in reference journals, 7 patents, has edited 3 books. He is recipient of MRSI, ICSC awards, Platinum Jubilee Lecture Award of Material Science Section of Indian Science Congress Association, Rajiv Goyal Prize of Young Scientist in the area of Physics, Material Research Society of India, Medal Award, CSIR Young Scientist Award, and Indian National Science Congress Young Scientist Award. Professor Khare is a Fellow of Institute of Physics, UK, Fellow of National Academy of Science, India, Fellow of Asia Pacific Academy of Materials, Council Member of Material Research Society of India, Member of Editorial Board of Superconductor Science and Technology from 2005 to 2008, and Member of Editorial Board of Current Physics Application from 2007. Sir, the stage is yours. You are the last speaker. Please enlighten us.
Okay, thank you very much, Dr. Datta, for this kind introduction. At the outset, I would like to thank Dr. Rajesh for inviting me to give a talk in this symposium. It's very interesting uh, to participate in this symposium. So I'm going to talk about this nanocomposite flexible films for harvesting mechanical energy. So why this work is done? So basically the content line is the following. First, I will talk about this motivation, that why we enter into this area. And then I will introduce a little bit about this polyvinyl difluoride material, which is a polymer. And this material we are using as a host material for making these flexible films. And then I will talk about this nanocomposite, what is the rationale in making this nanocomposite films. And then I will discuss about that, how these film can be used for the clean energy generation. Mostly, we have used this film for harvesting the mechanical energy. Okay, so if you see the current scenario, there are a lot of devices are coming which uses this kind of they are basically portable devices, and you require some kind of battery to power them. And right now, most of the devices, they use this lithium-ion batteries, and there are a lot of research are going on in the area of sodium batteries to have an alternative of the lithium batteries. And the way this progress is taking place is amazing. You see the number of smartphones which are quite now used. It's really amazing. And if you see, the number is really very large, and this is very challenging, that how we can make a lot of this storage devices to power them. And apart from that, because of IoT and all that, and many more devices are coming up, which are basically small power devices, and you need to power them. And it's very challenging to have all these devices powered in future by this kind of battery. So one has to look for the alternatives. And the alternative for, and obviously because of the environment constraints, we need to have energy sources which should not burden to our environment anymore. So the way it can happen, that we can have a solar energy, we have the hydrothermal, air energy, and all this work is going on, and there's been substantial progress in that. But there is another alternative which has been come up, and I'm going to focus more on that, is based on using this mechanical energy. If you see around, there are many sources of this mechanical energy. You see this AC, when this is running, there is a vibration is automatically taking place. There's a lot of movement of the traffics. There is a vibrations there. Even when we walk, our body movements give mechanical energy. Even the sea waves gives you mechanical energy. Wind energy also gives you mechanical energy. Even our heartbeat, the pulse beat, give you some kind of vibrations. Even when we breathe, that also gives some kind of low frequency vibration. So the idea is that if we can harness these vibrations in a useful way and convert them into electrical energy, then we can run some of the low power device. Obviously, these kind of sources will not generate very high kind of megawatt, kilowatt type of energy, but they can really give to milliwatt and microwatt of energy, and there could be a lot of devices which can be benefited from them. And so with that one motivation, we started working in this area. And if you see this, this slide shows this polyvinyl fluoride PVDF material, which we have used as a host material for making this flexible film. And it's a very interesting structure. This material can exist either in alpha phase or in beta phase or in gamma phase. And the difference comes in that in alpha, beta, and gamma, if you see the structure a little bit here, that the carbon gets attached with the 2 hydrogen or 2 fluorine. So we have CH2 dipole and CF2 dipole. And TG type of configuration. In that configuration, there is no net dipole moment exists here, and the material is not at all ferroelectric. Whereas if we have this beta phase, which is basically TTTT type of configuration, if you see here, there's a carbon which is attached with the fluorine, and if you see here the carbon attached with the fluorine and carbon attached with the hydrogen, so all them are aligned, so we have a permanent dipole moment here, and these materials start acting as a ferroelectric here. So in this PVDF material, if we have more percentage of the PVD beta phase, then this will behave as a flexible ferroelectric material. So this is the whole basis of making this nanocomposite material, that if we grow this PVDF material in place of other nanomaterials, how we can enhance this beta phase. So with that idea, we started working. And what was the motivation in this one? Instead of using because there are many piezoceramic materials like barium titanate, PZT, which has a very good ferroelectric property. But the problem here is that they are brittle and they are not flexible. And besides that, this PZT material, which is a very good ferroelectric property, they are not very environmental friendly. So that's why we started using this PVD material as a host and making this nanocomposite material so that the beta phase can be enhanced. Okay, so let me show you briefly how we make this nanocomposite films. If you see this view graph here, so we make this, one of the nanocomposite we tried with the making zinc oxide nano rods and adding it to PVDF matrix. And the way it is done, that first we make this zinc oxide material using this hydrothermal method, and then we make a PVDF film. And once we are making this PVDF film, we added this zinc oxide nanocomposite materials, zinc oxide rods, and then we drop casted this film, and the films are something like 20-25 micron thick, and inside this there is a lot of nanorods are there. Okay, so this is the zinc oxide PVDF nanocomposite, and if you see in this XRD, we see the characteristic of both the zinc oxide and also this PVDF material. Okay, and this is a SEM photograph, and SEM photograph you can see some zinc oxide nanorod on the surface also, but inside this matrix all this zinc oxide are embedded. And this is this FTIR picture of PVDF zinc oxide material, and which basically tells us that there is quite a good interaction takes place with PVDF and zinc oxide, which makes this nanocomposite films. And here is this surface topography of the film. This is also very interesting, and I will show you in a minute that once we have some applications, this kind of topography is very helpful. This is the PVDF film, and we have this zinc oxide PVDF. The surface topography gets more roughened, and not only that, the film also becomes more hydroscopic. The contact angle increases from 93 to 126. So it becomes more rough film, and also this topography also becomes, and this hydroscopic property also increases. Okay, so this is this PVDF zinc of this FTIR data. This FTIR studies we did to find out that how much is the beta phase and what happens when the beta phase, when we make this nanocomposite film. And what we observed that when we add this zinc oxide, this one, these started increasing, and we can get 75%. If they're more optimized things, we can even go to higher than 85% of this beta phase material in synthesis film. So the film becomes more ferroelectric, and for finding out the ferroelectric property, we studied this PE loop. And if you see this here, there's a black one is for the PVDF, whereas this orange and this one is for the nanocomposite film with different percentage of this zinc oxide. And this clearly shows that the nanocomposite film shows the higher ferroelectric properties. Okay, so the another things we did using this piezoelectric force microscopy study to find out more detail of this. And this piezoelectric force microscopy is based on applying some kind of pressure, and then we can find out the D33 parameters. And this measurement of D33 parameter is very useful to find out that how much the piezo property has enhanced once we have this nanocomposite film. And this is the tool we have used. This is basically atomic force microscope, in which this piezo trip is used, and this is used to find out this P loop at the localized point. And this characteristics we did, this P amplitude versus DC bias condition, and from here we calculated the D33 parameters. And if you see here, the D33 parameters goes to from 55 picometer per volt to 70 picometer per volt. So that D33 parameter get enhanced, which shows that these nanocomposite films basically have a higher piezo property. Okay, so there's more detail of KPFM measurements, how we did all these kind of things. Maybe at the due to shortage of time, I just skip to this. And there's another measurements we did for finding out this KPFM measurements, again by using this our atomic force workstation to find out what is the surface charges on this film. And these are very interesting things because you can find out the work function of this film. And once we have this zinc oxide PVDF film, its work function gets changed from 4.83 it goes to 4.57. So this the significance of this change in the work function you will see once we discuss one of the triboelectric application of this film for the converting mechanical energy into electrical energy. This enhancement, the change in the work function plays a very important role. This is another things we did again by KPFM measurement, that what is the surface charge on this film. So if you see, this is a PVDF film, and what we did, we rubbed this surface, and after rubbing again, we measure the surface charges. And if you see the vision here, the potential changes, and it goes from 0.53. And once we have this nanocomposite film, and we did the same experiment by rubbing it, then the surface charges changes a lot, and we have almost like change in the voltage 5.3, almost 10 times enhancement is there. So again, as I said, that these kind of things are very important when we want to use this film as a triboelectric application. Okay, so this is the, again more detail about this surface charges, etc. So we did all this kind of more detailed measurements to find out that what is the surface charges developed by this method. Okay, the another film we prepared using this sodium niobate and RGO PVDF nanocomposites. So again, the same procedure was used. First, we make this sodium niobate nano material, and then we make this nanocomposite materials. And the way it is done, that first we make this PVDF DMF solution, and then we added this sodium niobate, and we also added this RGO in this solution, and this finally we get this kind of flexible films. So this flexible film has both this PVDF and this reduced graphene oxide. And what is the significance of adding all these two? I will explain you in a minute. So this kind of flexible films are formed by this method. So this is the XRD measurement and this TEM measurement, which shows that the presence of this sodium niobate nanorod, this sodium niobate nanorod in the RGO nanocomposites, and again this with PVDF. Okay, so this is another again this XRD measurement and SEM measurement and FTIR measurements. And what we found from this FTIR measurement, that the beta phase of the PVDF film goes almost like 78% when we have this RGO and sodium niobate nanocomposites. And as I explained, that the advantage here is that since the beta phase gets large, we can have more piezo or ferro effect in this nanocomposite films. So what happens basically? You see in the structure of the PVDF, we have this CH2 and CF2 dipoles, and basically sodium niobate nanorods, when it is mixed with this one, it basically interact with CF2 dipoles and try to align them because of its own kind of ferro property. And similarly, this RGO basically react with interact with the CH2, and that also helps in the alignment. So that is how the beta phase of this material gets enhanced once we have this sodium niobate and RGO present in this material. Similarly, zinc oxide also, this interact with the CF2 dipoles and try to align them. Okay, so now comes to the application part. So one of the application that we have looked for these films for converting mechanical energy to electrical energy is based on this piezo effect. So piezo effect, as you know, that what happens whenever you apply some kind of a stress, there's some kind of bending. So because of that, there is a symmetry get disturbed, and we have a dipole get forms, and this because of this voltage get developed across it. So that is the principle of it. And the tribo effect is again much more interesting. You see, in your school days, you must have done this kind of experiment. You have rubbed this comb, and when this rubbing this comb is put on a piece of paper, it will start getting attractive. So this effect happens because of the tribo effect. And from a long time in the scientific community, this is always considered to be a negative effect. If any one of you have worked in a device, then you might have noted that if the device is very sensitive, like a FET or some kind of that device, we always worry that no, because of the grounding, etc., large current should not pass. And so we always try to ground ourselves before touching this device, so that this tribo effect don't take place. Otherwise, the device can get disturbed or get, in fact, destroyed. And you might have noticed that in winter, whenever we walk and touch our car, we get a shock. And this again, the tribo effect. Because of rubbing things and whatever the clothes, etc., we are making, wearing, some kind of very high voltage get developed. And once it gets grounded, some kind of current flows, and that gives us a shock. So in the device community, this has been considered to a very negative effect. In day-to-day also, we don't want to get a shock. But I am going to tell you that now started realizing that this kind of effect can be used very efficiently for converting mechanical energy to electrical energy. So one of the scheme I have shown here, suppose you have this PTFE and nylon, there are two materials, and you put nylon on PTFE, then because of the induced charges, there is positive and negative charges will decline, and there will be charge neutrality will be maintained. Now you start moving this top of the electrode in one direction, then what will happen? This negative charge will be there, but it will be unbalanced. And because of this, some positive charge will go from here to here. So because of that, there will be a flow of current. And if I slide invert again this charge will get balanced because of this positive charges, and this positive charges will move away. So we'll keep on getting kind of sinusoidal current if we keep on sliding to surface. So this is the basis of this. Again, the another mode we can do that we move this two electrodes with a distance and try to bring it nearer. Then again, the induced charges will be developed, and to balance this induced charges, some kind of current will flow. And if we move away, again, the current will flow in the opposite direction. So this is the way this triboelectric effect can be harnessed for generating electricity. So just to summarize this part, what we are planning to do that will increase the beta phase in this PVDF film. So the DT3 value get enhanced and becomes more piezoelectric, better piezoelectric material. And then you will use this for this piezo nano generator. And the another thing that we observed that in this film, the surface roughness increases, dielectric constant also increases, more hydrophobicity increases, and that really help us to make a better triboelectric nanogenerator using this field. So we have this, we can have this piezoelectric nanogenerator, we can have this triboelectric nanogenerator of using this kind of flexible film to convert the mechanical energy into electrical energy. This is a scheme that we have followed. Apart from that, what we have noted that this nanocomposite film is also good thermoelectric material. So we can also have a hybrid material in which this piezo and thermal can be used in one go. Okay, so let me first tell you about this piezoelectric nanogenerator. So this is our device. We have this our flexible film, which we have encapsulated here inside this two electrode, and then we have covered it And now when we put this device and start patting even by our thumb, this finger, then the voltage start developing here. If you see here in this picture, we have connected this device to a CRO. And whenever we tap on this device, we started getting voltage across here. And this voltage and this, the whole device can be connected to a circuit and it can be, the power can be stored in a capacitor, and then it can be used for lighting the LED. Or even directly also, these 2-3 devices can be connected to LED and it can be used for powering the LED. So for this kind of device, this zinc oxide nano PVDF film, we could get a power of something like 0.2 microwatt power we have got. This is a small power, but if we connect 2-3 devices in a series, we can get sufficient power for small power applications. And for this one, now I will just switch over to this triboelectric nano generator. So in this triboelectric generator, one of the scheme, as I explained you, that if I have these 2 electrodes and we start rubbing one over the other, we start getting the electricity out of this. So we have used this one electrode as PTFE, the other we have used this zinc oxide PVDF material. And this was a small scheme we have used for rubbing them. And when we rub this, we get a, so this voltage is very high. You see like 120 volt we get here. And this voltage, if you see only PVDF, we get something like 80 voltage, so it gets much enhanced once we have this PVDF zinc oxide nanocomposite films. And so we get a power of something like 10 microwatt type of power we get here. And this power, as I said, that if you have 2-3 devices coupled together, it's quite good for powering these small devices, small power application things. And if you have any sensor and we want to send data for remote sensor, we can do such kind of applications. Just to show you, demonstrate you a little bit more. So if when we are rubbing it, we are developing some kind of voltage and current, and this is used to power this LED. If you see the LED here, it's glowing because of the power which is generated by this rubbing this 2 electrode. We have tried this kind of device for several other applications, and the another geometry we have used is this geometry. This again a very interesting geometry. As I said, that one way of getting the triboelectric effect is rubbing one surface over the other. Other maybe can that we can bring this one electrode nearer to here, and then we can remove. In this process also, some voltage get developed here, and the current develops, and we get a power out of this. In this geometry, the advantage is that once we put pressure on it, some pressure is developed on this zinc oxide PVDF. And as I said, that it also gives the piezo effect. We get both the piezo effect and also the tribo effect together. And this is a hybrid device we have made. So we utilize both here, the piezo effect and the tribo effect in one go when we start pushing it from the top. So we have made this very light spring. So we have tested such device that if we take this device in a vehicle, and when we start moving, then because of this bad road, when we get a jerk, some kind of humping in our car, this is sufficient to generate voltage and the power, and this can be used for charging our mobile phone. Okay, so we are looking such kind of interesting applications. There are a lot of applications where we can do such kind of things. Just to complete this part, if you see, we have this piezo effect. We get an open circuit voltage of like something like 17 to 18 volt. When we have the tribo volt for this device, we get a 70 volt. But once we use this hybrid device, piezo and tribo, we get much larger voltage like 80 volt. So we have tested this device for simple applications. So we are going ahead. Many more applications. And as I said, that the work function of change of the work function of the material really helps in transferring the charges, and that basically is very conducive for getting a higher performance when we have this nanocomposite film. The another very interesting applications recently we have looked of using this tribo effect in the water. This is again a very interesting phenomena. You have water drops, and this water drops just falls on this nanocomposite films. And the water can have some charges, and once it comes in contact with this one, they will induce charges on this surface. So tribo effect takes place, and once the water drop start moving, because it will keep on rolling from one point to the another point, you have this voltage and current on this device. So we have fabricated such kind of device, very interesting. And if you see here, it's a zinc oxide PVDF film, we start getting a voltage of something like 0.2, 0.3 volt, and current in the order of 20 nanoampere, which is not very large. But as I said, that if we have many of such device in the series, basically we can get much larger output. And one of the things we did, you see, this is a demo here. The water is dropping on this one and water is going away. And because of this, if you see on the CRO here, we start getting this voltage. And we can also collect this current what we are getting. Similarly, if you see the water is falling on this one, we start getting this one. So we are really looking for many application of such kind of things. For example, if water is flowing, we can really get a energy out of nothing. So that's another things we are looking for such kind of device. See, water is falling, and because of this, in fact, we have tested that if the water is more salty or something, we get much higher voltage and current in such kind of device. Okay, so the last part of my talk, because I want to leave 4-5 minutes for discussion. So it's the hybrid device where we have used this, as I said, that PVDF zinc oxide material is also a thermoelectric material. So we have connected this hybrid material and this PN junction kind of materials, and also this PVDF zinc oxide materials just in one go. And in this one, when we push here, we can get this piezo effect. And when there is a change in temperature, we get also this voltage, thermal effect. So that is there. So we just demonstrated this device and we get a Seebeck coefficient, and we get this large and all that. So because open circuit voltage, even there is a 5 Kelvin difference, we get a kind of voltage which is 0.6 volt. Again, this single device, so it's not very large, and we get a piezo effect also. So we get 4-5 volt here. So we can combine these two things, and if we can have a very flexible device, 4-5 Kelvin is not a very large temperature. Even on our skin, when we're sitting in a AC or something, we get this kind of temperature difference. So we are planning to use some kind of hybrid device for converting this kind of mechanical and thermal energy in one go with this one. Okay, so with this one, I will stop. I leave 5 minutes for discussion because I was allotted 30 minutes for this talk. Thank you very much.
Thank you, Professor Khare, for your excellent talk. You have really showed us how a device can be prepared from PVDF, starting with the zinc oxide and then adding up other things into this. And this really is energy scavenging, which is very, very important field nowadays. So I'll ask our student coordinator to get some questions for you.
Sir, there is a question from Mr. Kunal. How
Yes.
can we change phase without changing temperature and pressure?
No, phase, you see, phase change takes place once we are making this material. So once we make this nanocomposite material, that's time itself, phase get changed. So at the final product, we have the beta phase much larger as compared to the original one. Okay, so when we do the temperature or pressure, then there is no change in the phase. When we do the pressure things, then this is piezo materials or ferroelectric materials, so you get a voltage across it, same as the piezo phenomena. Okay.
There is one more question from Professor Ramphal Sharma. How much the size of zinc oxides in your work making composites?
Yeah, we have used this zinc oxide nanorod, which is like 5 micron kind of diameter and something like 1 micron long wire.
You mean to say 5 nanometer or 5?
5 nanometer dia, and this length could be like a few hundred nanometers. Okay.
So the aspect ratio is important?
Yeah, aspect ratio is important because what happens, they get aligned and then it's easy to get charge separation more effectively. Yeah.
Okay.
Thank you, sir. There is no more questions.
Okay, thank you very much for listening.
Thank you very much, Professor Khare, for your wonderful talk. So now
Thank you very much, Dr. Datta, for conducting it here.
So now we come to the end of the second day session. Actually, it's the third day of a series of wonderful talks, starting with Professor Mulchandani and ending with Professor Khare, with a plethora of subjects, which definitely will enrich our faculty and students and whomsoever is really registered and listening to this webinar. So now I'll ask Shipra to take over and go for the next conclusion. Shipra,
Thank you so
please.
much. Thank you so much, Professor Datta. Thank you so much for the conduct of this session. This session was wonderful, enriching, and informative. It was so nice to get a thorough and holistic perspective of the latest research in the field. Thank you very much to our distinguished speakers, Professor Ashok Mulchandani, Professor Mahendra D. Shirsat, Professor Absar Ahmad, and Professor Neeraj Khare. On behalf of USBAS, I thank you so much for sparing your time and enlightening us with your views. Today's session is now drawing to a close. I thank you all for your gracious presence. We shall meet again tomorrow at 10:30 for our day 3 of the symposium. The eminent speakers for tomorrow are Professor Michael Lurch, Head School of Physics, Faculty of Engineering and Information Sciences, University of Wollongong, Australia; Professor Atul Khanna, Department of Physics, Guru Nanak Dev University, Amritsar; Professor P.D. Sahare, Department of Physics and Astrophysics, University of Delhi; and finally Dr. Mengling Sai, Department of Material Science Engineering. The session is now coming to its end. Thank you one and all. See you tomorrow.